Today, I am talking with Daniel Whiteson. He's a particle physicist at UC Irvine and an active researcher on CERN's Large Hadron Collider. Every 24 nanoseconds, his team smashes protons together and waits for the universe to show them something new.
Oh, CERN, huh? The place with the Shiva statue out front and the interdimensional portal out back. Oh, yeah, I know the place.
His new book is called Do Aliens Speak Physics? And the question it asks is wild. Is physics something we discovered, or is it something we invented? Because if it's invented, aliens might show up one day with a completely different version, and ours might be wrong, or at least incomplete. It's hard to explain in an intro, but it's pretty wild. We also get into some places I didn't expect to go, like what happens below the Planck scale.
Oh, below the Planck scale. That's where the lizard people keep the good stuff.
We also get into why dark matter might have its own version of the Higgs boson, and why a philosopher named Hartree Field re-derived gravity without using numbers. No math. We also talked about how your phone is secretly a cosmic ray detector, and that's true. Daniel built an app.
You know who else built an app that tracks things from space? The NSA! But at least they had the decency to lie about it. Humans are such sheep.
Anyway, this was a lot of fun.
Sheep.
Let's go down to the basement. Hey, you can watch the Y-Files on Spotify. New video episodes every Monday and Friday. And premium subscribers get fewer ads, which means fewer interruptions when things start getting weird. Daniel, welcome to the basement.
Thank you very much for having me. So excited to talk to you about all of this crazy stuff in science.
Me too. So yeah, we're going to get to some of those baffling secrets of the universe. But here's one I really want to know. What is the secret to making a killer Nutella nut roll? Like, how did you become famous for that?
A killer Nutella nut
like,
roll?
I heard that you have a strong baking game.
I do. On my CV, for example, I have a cookie recipe. You have like list of awards, papers, favorite cookie recipe. I put that in there actually just to see if anybody's like reading that at all. And I'll sometimes get an email from somebody who's like, hey, I tried your recipe. It's pretty good.
What is it? What's the cookie?
It's chocolate chip oatmeal cookies with tahini. That's the key.
That's
tahini,
the key?
Absolutely. I love tahini. I'm a sucker for halva or anything with tahini and its sesame seeds. That's my kryptonite.
We're going to try that. I always heard that baking is science.
Yeah. It's
right?
chemistry, right?
Yeah.
There's transformations, things change phase. It's incredible what happens there. And it's a great example of like emergence. You know, you see stuff happening on the bigger scale, like this dough turns into cookie. You don't know what's going on underneath the microscopic details of what's happening with all the baking powder and the vinegar and whatever. It's like magic to you, right? There's some microscopic detail and then boom, it turns into a cookie. And you don't always have to know. You don't always have to care. But it's incredible. You have this like experience on the macroscopic scale, and then there's like all this stuff happening underneath.
Were you baking before you became a scientist, or did you say, you know what, I've got an idea?
I've got a sweet tooth.
Okay.
And I love gluten. So I've
Who
been baking
doesn't?
forever. I know gluten is God's gift to humanity. Yeah.
All right. Another question that I need to know. What's your favorite video game that you programmed? That you programmed. Didn't you?
Yeah.
You were a coder.
I am a coder. I was a coder. I started programming in BASIC on a Commodore VIC-20, right?
Same.
You like tiny amount of RAM, and you stored your programs on cassette tapes.
Yes.
Yeah, I'm OG programmer. I remember when my dad brought home our first computer. It was transformational for me. And yeah, I wrote Tic-Tac-Toe was my first game.
Okay.
First you write the 2-player version, and then you're like, I want to play against the computer. How can I program a little bit of computer intelligence in there? What is the strategy for Tic-Tac-Toe?
Did you use like ASCII characters?
Yeah.
Refresh
absolutely.
the page. Refresh the page is CHR $147 if I'm not mistaken.
Yeah, and eventually you realize, wow, tic-tac-toe is not that complicated a game. You can beat a computer. You can write a computer player that's unbeatable, that can't be beaten. And then you get interested in like deeper games, write checkers, write chess.
Now,
Those
hold
are
on
really
a second.
hard.
I've got to challenge you because didn't Whopper tell us that there is no winner to tic-tac-toe? Do you know what I'm talking about?
Whopper was the game show on
No,
TV?
that was the big computer in war games.
Oh,
Remember
right.
where the only...
Shall we play a game?
Yes, the only strategy is not to play.
Yeah, that's right. Yeah.
So
Everybody loses in global thermonuclear war.
Yes,
I still believe that
does.
one. Yes,
It does.
yeah. But if you play tic-tac-toe right, you should get a draw every time.
Right.
And that was something I only discovered by writing a computer player that I couldn't beat, which was pretty cool. Yeah.
Vic 20, when I'm talking to other... can I call you a nerd?
Yes, I'm a proud nerd. Absolutely.
Same. When I'm talking to other nerds, we always have this competition about who started at the lowest baud rate. Lowest baud rate when you first dialed up to CompuServer BBSs. What's your lowest baud rate? Let me see.
Yeah, I ran a BBS actually.
You
out
did?
Of my home, yes.
No
I had one on my computer.
On
Absolutely.
mom's phone line.
On mom's phone line. We racked up a bill. Yeah, we had a second phone line actually.
Wow.
And we had people all over the country, all over the world contributing. It was a lot of fun. I was so enamored. That was, this is well before Ethernet in your house, right? Everything is dial-up, and so I think it was 14.4 kilobaud was my slowest.
That was your slowest?
Yeah.
Oh boy, I go
Yeah.
back to 150 baud.
Wow.
But I'm
incredible.
a lot older than you. I'm in the presence of a sysop. That's amazing.
Yeah.
What got you? It started in that because Vic 20 is, I think that came out in 81 or close to it. What got you started in computers that early?
Yeah. Well, my dad was working at the lab in Los Alamos, so I grew up in northern New Mexico.
He was working at Los Alamos.
Yeah, absolutely.
In the early 80s. I have questions that I probably can't ask.
And I probably can't answer.
Was he doing secret stuff for the government?
Yeah, he had a Q clearance, and so did my mom, and both of them worked at the lab, and I never saw their offices. I don't know what they worked on. They were always behind the fence.
Wow.
Yeah, absolutely.
They never told you anything? I mean, not classified. What did they say they were doing there?
Well, I knew my mom was working on nuclear non-proliferation. I know my mom was working on nuclear non-proliferation stuff very generally.
Mm-hmm.
And my dad, I had no idea. He actually went out to the test sites in Nevada sometimes. So he was working on definitely weapons-related stuff. But that's one reason why when I got into physics, I decided to work on something that could not be turned into a weapon. Like, as far as I know, nothing we develop at CERN could be used to kill anybody. Because, developing weapons of mass destruction and pointing them at civilian populations, I respect that my parents worked on that. And
Sure.
Somebody has to do it, but it's morally complicated,
It is. I wish we didn't mess with that at all.
Yeah. But they came to it from a funny path because they actually met in Israel when they were Orthodox Jews. My father was a rabbi originally. And then he lost his faith, and we moved to the U.S., and he went back to school, became an engineer, and then we went to the lab. And so he was around computers, my mom was around computers, and they brought one home, and I started playing with it and got hooked. The power of this thing, and you could connect to people from around the world. It's intoxicating.
It's intoxicating.
Yeah.
Oh my God. It's a very similar experience. I think I ran into a computer at a furniture store and they were using it as a prop.
Wow.
And they just let me sit there for hours. And I was like, Mom, I need to have one of these. And it was a VIC 20. Then you go C64, then you go 500. That's how he did that.
Yeah.
You had to go Commodore 64, right?
Eventually, yeah.
Okay.
We upgraded, and then we got a PC, of course.
Of course.
Yeah.
Commodore 64. When you got that floppy drive, which was the 1541, was it just like, how do we even fill this thing?
Right? I know. This is so easy now. You have all this RAM, and you can write all this stuff to disk, and yeah, everything became so easy. But every time we upgrade our computers, we create more possibility for what we can do. And there's never a limit, no matter how powerful our computers are, somebody's going to think of something which requires more computing.
Yes.
And it gives us more power to explore the universe. It's incredible to me now how much of what we do at CERN, for example, is powered by computers. We just could not do it without computers. It's in everything we do. It's enabled so much of what we understand about the universe.
And you're writing code there, which I think you said you enjoy doing.
I do, yeah. I have a big research group, people under me carrying out the details of the research, but there's always one project where I'm the one writing the code, making the plots, responsible for the progress, because that's why I got into this, not to like manage a group and do spreadsheets, but like investigate the universe and be there at the moment when you get to ask the question and hear the answer. I never want to give that up.
So I think most people understand how particle acceleration works. You smash them together.
Yeah.
That reminds me, you're smashing atoms together. As a kid, weren't you smashing rocks together? You were doing this for a long time, weren't you?
Yeah, absolutely.
Could you tell me, that was when you were a kid, right?
Yeah, when I was a kid, I was wondering, what is everything made out of? You take two rocks, you smash them together, what do you get? You get smaller rocks.
Yes.
Cool. Smash those together, what do you get? Smaller rocks. And I'm wondering, how long can you do this for? Right?
You and Plato are the only ones.
Yeah, well,
okay.
At some point, you just keep getting smaller and smaller rocks, or at some point, is it stop being a rock and it's something else, right? And I just want to where my brain goes. I'm more interested in like the foundational, fundamental questions of things, because to me it sets like the context of our lives and why everything is this certain way. And so I wanted to get down to the nitty gritty, from a very early age. And so to me, the Large Hadron Collider is like the ultimate rock smasher.
Of course.
Yeah.
So you've always been interested in the building blocks.
Oh, yeah.
Even before you even knew what they were.
Yeah.
That's
absolutely.
really interesting.
And I feel like everybody has a question where if you could speak to an oracle or to God or to advanced aliens and they give you one opportunity to learn something about the universe, everybody has a question that they want to know the answer to. And it's different. The marvelous thing about human curiosity is that everybody has their own question. That's why some people are working at particle colliders because they want to know what's the smallest thing. And other people are building telescopes to look for aliens because they want to know, are we alone? Or somebody else is like sloshing through the rainforest, trying to understand how spiders make their webs or whatever. Human curiosity is so varied and powerful, and it's in everybody.
That diversity is very important.
Very important.
Then what's your question?
Yeah, my question is, what is everything made out of, right? Fundamentally, what defines the building blocks of the universe? Is there a lowest level, like a firmament from which everything bubbles up, or does it go on forever?
Ooh, we'll get into that a little bit in more detail later, but are you talking like, do you sit there and go, maybe there's something smaller than the Planck number?
Yeah, for sure. Absolutely.
Really?
I think the Planck number is widely misunderstood.
Okay.
People talk about the Planck scale.
Yes.
Like it's, the resolution of the universe. What is the Planck scale? You take a bunch of constants, you multiply them together, you get a distance. That's the Planck scale. It's like 10 to the minus 35 meters. What's true about the Planck scale, which is often said, is we can't know anything smaller than 10 to the minus 35 meters with our current understanding of physics.
Ah.
Okay, so what happens there is that we have two pillars of physics: quantum mechanics, which describes little particles and how things move, and general relativity, which describes gravity and space and all that stuff. Mostly, they don't intersect because you're either talking about big stuff for relativity or small stuff for quantum mechanics. Right. But at 10 to the minus 35 meters, you need both of them. And those two theories, we don't know how to get them to play well together. Like, there's no theory of quantum gravity that makes them come together in harmony. They disagree. They disagree about the nature of space, about the nature of time, about everything. So we have these two pillars of physics, and mostly they're fine, but sometimes they overlap. And at 10 to the minus 35 meters, we don't know how to proceed. That doesn't mean that there's no explanation for what happens below 10 to the minus 35 meters, or that there can't ever be. It's just like the current horizon of our understanding. So you see people say, like, that's the pixel size of the universe.
Yes.
It's more like the limit beyond which we cannot predict with our current theories. But tomorrow, somebody makes string theory work or comes up with a new theory of quantum gravity that predicts past that point. Boom, now we can see deeper into the history of the universe and into the very, very tiny. So it's not a fundamental limit at all of our understanding. It's a limit of our current theories, which, of course, are not the final story.
Is that a common opinion among physicists, or are you? Because I've heard you say that we only understand 5% of physics. I don't know if every physicist likes that number, but in that 95%, is unified field theory in there? Do your gut?
Yeah, so there's a couple of questions there. I think that almost every physicist sees that the same way, but there's often a gap between the way physicists see their work and the way the public understands it. The way like mass is misunderstood and black holes are misunderstood. The Big Bang is widely misunderstood and misexplained. So I think that almost every physicist would agree with me that the Planck scale is not a fundamental limit to our possibility of understanding. I think that's pretty widely understood inside physics, though in popular science, it's not often described that way. And it frustrates me that there's this gap between what physics has revealed about the universe and how scientists think about and talk about it, and how it's described and understood in popular science. And that's unfortunate because I want people to know what is the real story, what are scientists thinking, and I respect that sometimes that has to be translated, and sometimes those translations go wrong for good reasons and with good intentions. Absolutely, it's hard to translate it. But when there's that persistent gap, I feel like that's unfortunate because people are being not intentionally misled, but they're misunderstanding what we know and what we don't.
That's why I encourage everybody to check out your podcast because you and Kelly do a great job of making this accessible. It's also super fun. Like you guys are funny.
Time. Yeah, Kelly's a great friend of mine. She's a great scientist, and it's just two people talking about science. And we talk about topics that she understands, and so I'm learning about biology and the history of cholera. And we talk about stuff that I understand, and so she's learning about particles and dark matter in space. And then the listeners get to learn about a huge variety of topics in science. And I hope have a good time at the same time.
So to get smaller than Planck, is there an experimental way to do that?
Yeah.
Or I don't know. Look, you know how they say there's no stupid questions?
Yeah.
Today you're going to get a lot of those.
No, there are no stupid questions. It's a great question. It's an important question because, physics has more than one branch to it. It's got the theoretical side, like how could the universe work? And that's really important. And often we feel like the answers are there. But it's also got the experimental side, which is going out there to just ask the universe, hey, show us how you work. But, that requires effort. It requires cleverness. Sometimes people think all the smart guys are in theory, right? But the experimentalists have a different kind of cleverness because they have to force the universe to reveal the answers. You can't just sit on a rock and think your way to the understanding of the universe. The Greeks tried that, right? Didn't make a lot of progress.
Right.
You got to force the universe to reveal it, which means coming up with clever situations where if the answer is A or B, you'll get a different outcome, right? That's the whole idea of experimental physics is how do we force the universe to show us? But we're limited with our tools, right? And the frustrating thing about understanding general relativity and quantum mechanics is that mostly it's hard to bring them near each other. So if we could see inside a black hole, we would know the answer to how do you unify general relativity and quantum gravity and quantum mechanics. We can't see inside a black hole. Too bad. If we could see the early universe, we could as well, because the early universe had a stage where things were denser than the Planck scale. The Planck scale you can express as a distance or as a temperature. And so things were hotter than the Planck temperature.
And a time as well, yeah?
Yeah, absolutely.
So when you say the early universe, we know that Big Bang, acceleration, everything happens. Are you talking about that first femtosecond? Before what happened right there?
Right, exactly. So this is all related to what we were talking about earlier. And I think the Big Bang is deeply misunderstood. So let's be very careful about what we mean when we say the Big Bang and what we mean by a certain time. So, we know the universe is vast and it's pretty cold and it's pretty dilute. But when we look back in time by looking out into space and seeing how things looked earlier, we see it was denser. So the universe is less dense now, it was more dense in the past. You rewind the clock, what happens? Things get denser and denser and denser and denser. And our theories work really, really well predicting things when they get all the way up to a certain temperature or a certain density. And that's the Planck scale. That's the Planck temperature. That's the Big Bang, is the expansion of the universe from that Planck scale density, which, and going earlier, that is another thing, from that Planck scale density up till now. That's the Big Bang. The Big Bang is widely misunderstood as the universe began as a point in space and it exploded out into existing space. That's what most people's impression of the Big Bang is, and that's basically totally wrong,
Sure.
though widely described that way.
Of course.
It's wrong because the Big Bang doesn't claim to just explain the origins of the universe. It's not the beginning of time. It says, look, we understand from this point forward how the universe expanded and cooled. Before that, big question mark. We don't know. Yeah, that's part is speculative. And there are lots of theories there we can dig into, but that part we don't know. So everything from Planck scale forward is the Big Bang. Before that, question mark. So we don't know how the universe began. The Big Bang does not claim how the universe began. It does not. It's agnostic on that question. And the other thing people don't understand is there was never a point in empty space. The Big Bang was everywhere. The whole universe was always filled with stuff. So,
Wait, hold on. The whole universe was the universe was there, and I have to put there in quotes, before the Big Bang?
So we don't know where all the stuff came from.
Right.
There's some hot, dense state 13.8 billion years ago, unexplained.
I'm singing the theme now to Big Bang Theory. Okay.
That the universe then expanded and became more dilute, less dense.
Right.
So the Big Bang is about density. Right. Now, if the universe is infinite today, and we don't know, but let's say that it is, then it was infinite then. Because you can't go from a finite universe to an infinite universe.
Right.
So that means if we start with an infinite universe that's big and not very dense, and we rewind the clock to an infinite universe that's dense, it's an infinite universe filled with infinite matter. It's an infinite Big Bang. The Big Bang was everywhere. It was not an explosion of a point out into empty space. There was no empty space. It's just all of space is already filled with stuff. Now, people listening are going to be like, okay, but where did that stuff come from, right? You can't just say we don't know. And we're not just saying we don't know. We're saying the Big Bang doesn't explain that. It's not an infinitely dense point which exploded out into space. Lots of theories about where that stuff came from, inflation, etc. But we don't know if there was a beginning. We don't know if that goes on forever backwards in time. We don't know what happened there. And so when I say, maybe the early universe can help us understand how to bring general relativity in harmony with quantum mechanics, I say that we could just watch it. If we can look and see what happened before the moment of the Planck density, then we could know. And so that's hard, right? Experimentally, that's very, very challenging.
Of course. I've heard everything from quantum foam to in the beginning.
Yeah.
So where, if you had to, we're going to do a lot of speculation today.
Sure.
Where do you go? Where do you lean?
Yeah, well, we're going to know. We're going to figure it out.
We are?
We absolutely are. I have confidence. Look, humans are clever, right? And when we want to know, when we are driven by our curiosity, we're going to figure this stuff out. And anytime somebody tells you this is impossible to figure out, that just means we haven't been smart enough yet, or the right kid hasn't been inspired yet. And that's, one reason why I want people to understand what we don't know about science, because there's some kid out there who's thinking, oh, science is mostly figured out. I'm going to go and be a rock star instead. And no, I want that genius to come crack these problems, to be inspired by the mysteries. But, we have a path forward already. Like the earliest thing we've seen in the universe is not from t equals 0, the moment of Planck density. It's like 400,000 years later. That's when the universe became transparent. Universe was hot and dense like the center of the sun. So if you made a photon, it just got reabsorbed, right?
Right.
Like if you turned on a flashlight in the center of the sun, the beam is not going to get to Earth, right? The sun is opaque. The universe was opaque. And then it became transparent. And light created right at that moment when the universe became transparent is still around. We can see it. Incredibly powerful scientifically, tells us about the early universe and proves that there was dark matter already back then. Amazing. But that's like 400,000 years after the point we're interested in. How do we go deeper? So the key is that the universe was opaque to light before that point.
Right.
But, the universe can be transparent to other stuff. For example, neutrinos. Neutrinos can pass right through the Earth. There are neutrinos passing through my fingers right now, like a trillion every second pass through my fingernails. So
can they exceed the speed of light?
They cannot.
They can't.
No,
Okay.
Nothing can exceed the speed of light, and they have a tiny little bit of mass, so they move just below the speed of light.
Okay.
Yeah, but they were flying around the early universe. And the universe was transparent to neutrinos just like a second after this Planck moment. So if we could see neutrinos from the very early universe, we could see 400,000 years earlier than we've ever seen before. We could see the structure of the universe, the shape of the universe, what was going on. Was it foamy? Was it smooth? Were there purple dragons? We don't know. That's exploration, right? We have ideas, we have theories, we can use, our ideas to figure it out, but the best part of science is when you're surprised.
Yes.
Right? When you ask the universe something and the answer is something nobody expected. Those are the reasons I got into science, for those moments, right? When you're like, what? That's the way it works. Nobody expected that, right? And so, my scientific dream is that kind of discovery. When the universe tells you the answer and you're like, that can't be. It's impossible. And yet it is, which means us tiny little humans have to change the way we think about the universe. And that's the power of experimental physics, is that it's our connection to reality. And we can go beyond neutrinos. There are gravitational waves from the very early universe. And the universe is mostly transparent. Mostly transparent to gravitational waves from very, very, very early on, fractions of a second. And people are looking for those. And people are looking for those neutrinos, and they'll find them. And so I think, in the next years or decades, we'll learn a lot more about the very, very early universe. And then people will have a better idea of how to go even beyond that to, before the Planck density. And somebody out there is going to figure that out. And we're going to learn how to unify quantum mechanics and general relativity and how the universe actually works.
You're confident that we'll get there?
I think we're going to get there. I mean, I don't know for sure. I like to be optimistic. I can't guarantee it. There could be a limit to human cognition. Maybe we're not smart enough. But, maybe the aliens will show up and they'll tell us. Or maybe we'll stumble into it before they get here. I kind of hope that we figured it out. I would love to be there for it. But, the rate of progress of scientific discovery and understanding is astounding. It's just accelerating. So I wouldn't bet against humanity.
What's the practical way to make that observation? I mean, what's the machine? How do you look back that far?
Yeah, so in terms of astronomy, you just need to look out into the universe. Neutrinos are really hard to spot because, as we say, they can pass through the whole Earth without interacting, which means, if we're transparent to neutrinos, that they're invisible to us. But they have a tiny chance of interacting. So we have neutrino detectors, essentially huge underground vats of liquid that are very, very quiet. And we wait for a neutrino to pass through and to kick one of those atoms in a particular way so we can tell there was a neutrino there. And these neutrinos from the very early universe are very hard to spot. They're lower energy than the neutrinos made by the sun. So it's a challenge, but it's an experimental challenge. We just need to build bigger neutrino telescopes, these underground vats of liquid that can see neutrinos. So they're sensitive to the very rare, the very slow, the very quiet cosmic neutrino background. And the same thing with gravitational waves. We have space telescopes that look for these signatures, these ripples. We have detectors that look for gravitational waves. We have even strung together stars. We have a galaxy size gravitational wave detector built out of all the pulsars in the galaxy. It's really an incredible piece of science.
Built out of the pulsars. Okay, just to quickly explain what a pulsar is, because those are amazing.
Yeah.
And when talking about pulsars, I start to feel like maybe we don't even understand time completely, because how quickly they rotate and all of that. So what are they, and how do you use that to detect anything?
Yeah. So pulsars are neutron stars, and stars have a life cycle. They burn, fusion happens within them. Eventually they use up their fuel. Sometimes if they're big enough, they turn into black holes, or they turn into white dwarfs. If they're not big enough to turn into a black hole, they can also turn into neutron stars, which are just a hot, dense clump of stuff spinning really, really fast. Really dense, like a teaspoon of neutron star weighs an incredible amount. I don't have the number at my fingertips. It's super dense matter. Pulsars are a kind of neutron star that have a very strong beam of material shooting up from the poles. So neutron stars have a magnetic field, and the way that we see the northern lights, this is particles from space that get funneled by our magnetic field up to the North Pole and down to the South Pole. Really cool. The inverse can also happen. If you're emitting a beam of particles, your magnetic field will turn that into a beam that comes from the North and the South Pole.
Ah.
And so if you have a neutron star and it's spinning and it's got a magnetic field that's not aligned with the spin of the neutron star, just like our magnetic field is not perfectly aligned with how the Earth spins, then you have a beam, and that beam is sweeping through space, right? Because the neutron star is spinning and the magnetic field is spinning, it's precessing. And sometimes it passes over the Earth. And so you get a blip of that beam and then it goes away. Then you get a blip of the beam when it comes back around. So those are the pulses of a pulsar. And they're incredible because they're super duper precise. Like they rotate with an amazing regularity. Sometimes they take a second to spin. Millisecond pulsars are these incredibly fast spinning stars that every millisecond we get a beep from them. And there's great stories about their discovery. You know, they saw them in the sky and they thought, what is this thing beeping at us, right? Is this aliens?
Right.
Are these the aliens?
I think Tesla misunderstood a pulsar as a message at some point.
Oh, okay, cool.
So how do you use those to detect stuff?
Yeah, so they are clocks. They're clocks out there in the universe. And gravitational waves are distortions in space and time, right? They are ripples in space-time. And so if you have a gravitational wave passing through the universe and it passes between you and the pulsar, it's going to affect the pattern of the pulses, right? You're going to see this blip, 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 and it's going to be, one of them is going to be a little bit longer, another one's going to be a little bit shorter. So you can predict how a gravitational wave with a wavelength the size of the galaxy is going to affect how you see these incredible clocks that the universe has put everywhere. And so if you make really careful measurements of all those pulsars, you can reverse engineer what happens to that gravitational wave. And they've recently seen this a few years ago. Really incredible pulsar timing arrays. And like, this is what I mean by the ingenuity of experimental physicists. Like, you can't just build a device the size of the galaxy to measure these things. You got to figure out what's out there and how do we use it to reveal the truth to us.
That's brilliant.
It's brilliant stuff.
So since that worked, what did that mean? Why was that so important?
What it means is that we learned that there are gravitational waves out there that are, wavelength the size of the galaxy. The gravitational wave detector we built on Earth, LIGO, it can see gravitational waves of a certain wavelength, but it can't see the really, really big ones. And that's the kind of thing that is going to tell us about the very early universe. So right now they're just saying, oh, there are gravitational waves out there with huge wavelength. And it's kind of a noisy environment because anytime anything in the universe moves, it makes a gravitational wave. Any acceleration. I wave my hand, that's a gravitational wave.
Sure.
Any black hole orbiting anything else, that's a gravitational wave. So we've discovered the universe is kind of noisy in gravitational waves. There's a lot of shouting going on, and we got to pick out exactly the voice that's telling us about the very, very early universe. And that's a challenge. And, it's a needle in a haystack, but, I'm counting on humanity.
I wish I was as optimistic, but that's fine. That's fine. I want to get back to gravity in a second, every physicist's memoir, but what's it like at CERN? You go in, you got your thermos, you punch a clock. We all know what it is, but what's it like to be there and spend a day there?
It is so exciting. It is the center of the world for particle physics. It's like the nerd capital of the world. Everybody is there and they're buzzing with excitement. When the machine is running, you never know what day is going to be the day you make a discovery, right? Every day could be like, look what we saw in the data. Look what the universe delivered. Something I think a lot of people don't understand about the collisions at CERN is that we do the same experiment over and over again, right? It's two particles, very high energy, smashing against each other. And every time we do it, every 24 nanoseconds, the universe decides what comes out.
Every 24 nanoseconds?
Every 24 nanoseconds, there's a collision.
Okay.
And quantum mechanics tells you that you can do the same experiment twice and get two different outcomes.
Essentially infinitely and get all the outcomes.
That's right. That's exactly it. We don't know what the universe can do, but if we do the same experiment over and over again, eventually everything it can do is revealed to us. And that's what we want to know is like, what can happen when you smash two protons together? If you're thinking of protons as like little billiard balls and you think, well, if I smash them together, then they're going to bounce off at a certain angle and the initial state determines the final state. That's classical physics, right? The initial state determines the final state. You take the same shot and pool over and over again. If you're really precise, you get exactly the same outcome. But quantum mechanics says what's predicted, what's determined is not the outcome, but the probability of various outcomes.
Right.
And that's how we explore the universe with collisions, is that, we're looking for things that are really, really rare. Once a trillion, once a quadrillion collisions. And you do enough collisions, eventually the universe will show you the rarest of rare things that it can make. What's on its secret menu of what it can do. The things that I want to know, like what is the smallest thing? What is everything made out of? What is the heaviest thing? And so it's exciting to be at CERN. It's also really fun. Like the cafeteria at CERN is filled with people from all over the world. You hear like Italian and English and Japanese and Romanian, and people are eating all sorts of weird foods. And probably the best summer of my life I spent as a student at CERN when I was very, very young.
Really?
Yeah, hanging out with a bunch of Italians who taught me Italian and how to cook and bake and make pizza, and drinking with the Czechs. And it's just a wonderful, wonderful place. It's open, it's collaborative. CERN was built after World War II as an effort to hey, let's connect scientists from around the world so we're all humanizing each other and we're not like building weapons of mass destruction to point at each other, right? It's all about peace and science and harmony. And, there's arguments for sure. And it's fun to learn how different people argue. When somebody from Italy tells you no, it means something different from when somebody from Japan tells you no, and you learn these things. And it's fun to hear people argue in English and all sorts of different accents. It's fun to argue with people about where do you put a comma in this paper?
Don't get my wife started on the Oxford comma.
Well, we have 5,000 authors in every paper, which means everybody gets to weigh in on the comma. So the comma goes in, the comma goes out, the comma goes in, the comma goes out. It's comical, but it's a lot of fun. It's really exciting. Every time I go to CERN, I'm just reinvigorated by the possibilities, what we can learn about the universe. It's incredible to me that we know how to find the secrets of the universe. We just have to go do it. If you gave me $100 billion, I could build you a collider that would reveal secrets of the universe. We just have to do it. We just have to decide. If we built new space telescopes, we would see things in the early universe that would shock us, that would blow our minds. It's happened with every time we build a telescope. We see something that goes, what
every
is that?
Time.
Right? And these things are cheap. On the scale of countries and GDPs. Sure. So we just have to decide to do it. And the universe is there and waiting for us to decide we want to know its secrets.
But Daniel, if we build all these colliders, how do we fund our wars? How do we have to choose. Oh my goodness.
I don't think we have to choose. Actually, I don't think we have to. I think it's not a zero-sum game.
Agree.
Every dollar we spend on science comes back to us twofold, tenfold, 1,000-fold. It's a good investment. I believe in America. I believe in humanity. I believe in people. I believe in smarts. We should invest in ourselves by spending money on basic research. It's the best investment you can make.
Honestly, and the more we learn about the universe, and I don't mean that as just as a fortune cookie. The more we actually learn, the fewer conflicts we're going to have.
Yeah. Yeah,
Aren't
I hope
we?
so. I hope that's true. I'm not a politician and I'm not a sociologist, but I do think that understanding the universe is something that brings us all together.
Yes.
We're all curious. We all want to know answers. And I've worked with people from, 172 different countries, and we're all just people. We're all just curious about the universe, right?
Yep.
It definitely brings us together.
How much data are we talking about every 24 nanoseconds?
Every 24 nanoseconds, we read out 100 million channels of data about the collision.
Wow.
And so it's an enormous tsunami of data, so much that we have to throw most of it away.
Why do you throw it away? Because you already know what it is, or because
it's too much to ever analyze? We couldn't effectively store it to tape and search it. And also most of it's boring. Most of what happens when you collide protons is they bounce off each other and stay protons. Yawn. We've seen that a million times. So we're interested in the rare stuff. So we have a filter at the very, very early stage that decides keep it or kill it. And that makes downstream analysis much more efficient because you don't have to search through all the boring stuff to find the interesting stuff. But it means also we have to be smart about what we're keeping and what we're killing. That's actually what my team works on. And I found that super fun. You have to make this super fast decision and you don't have a lot of time to do a lot of really fancy calculations. It's kill it or keep it every 24 nanoseconds.
Right.
So high-speed computing, I thought, was a really fun challenge.
How do you know you're not throwing out the next Nobel Prize?
Yeah.
I mean,
Yeah.
if we're talking, I'm assuming you're using machine learning or AI of some kind.
Well, the very first stage is very simple.
Okay.
And then it gets more complex. And we're definitely using machine learning and AI. We don't know that we're not throwing away some, treasure out with the garbage. But we do have some filters that just randomly select events. Let's just keep, 1 out of 1,000 randomly. So that if there's something crazy that we didn't expect, we'll probably find it there. But we just can't keep all of it. It's just too much data. We're talking about petabytes and petabytes every day. It's insane how much data we produce.
How do you train machine learning if you don't know what you're looking for?
Yeah, this is a big question in machine learning and more broadly in artificial intelligence. It's a whole field called anomaly detection.
Okay.
How do you find something that's out of the ordinary if you don't know what you're looking for? Because that's what I want, right? I want to find the big surprise, the thing that makes us go, what is that even? And so we have techniques there. Anomaly detection says, well, let's learn to describe what's expected, and then we'll think about anything that's different from that. And so you train machine learning, you give it a bunch of examples, you say, here's the kind of thing we're expecting. Figure out how to think about that so that if we give you something you haven't seen before, you can flag it. And so what machine learning does is, for example, it takes all the things that you don't or that you aren't interested in, and it learns to transform that into some internal mathematical space and then transform it back. And it becomes really good at doing that for the kind of things you've been training it for. And then when something new and weird comes, then that transformation fails. It's like, well, I don't know how to transform this there and back. And so it's just an example, but there's lots of ways that you can train machine learning to flag something unusual. But it's hard, and you never really know if there's something there that you've missed.
It's got to bother you a little bit,
Oh,
right?
for sure. Keeps me up at night.
And we might have thrown out the one thing we needed, but we don't know.
But that's always the case because we always have to make decisions about what kind of thing to look for. I'll give you another example. When we analyze our data, we're looking for particles that come out of the collision. And we expect particles to move in a certain way because they have electromagnetic charge and they have a magnetic field, and we can use our physics to say, okay, particles always move in this particular path, a helical path. And if you look at pictures of collisions, you see particles whizzing out in these spirals.
Right.
So spirals are everywhere. And most of our software that looks for particles looks for spirals because we expect everything to move as a spiral. So
and is that what you're mostly
those.
analyzing? Is just the paths of the particles from the collision? That's what it is. Okay.
Exactly. Because the thing we're looking for, like the Higgs boson or something else new, it only lasts very, very briefly, 10 to the minus 23 seconds. So you never see it directly. You see what it turns into. So we see these spirals, we see the particles, and we say, okay, that looks like there was a Higgs boson there. But it's not like I can say, oh, here's a Higgs, or here's a handful of them, or I got a bunch of them in a box, right?
Right.
We can only say that there probably were there based on the path of these particles. So figuring out the path of these particles is important, but we only tend to look for these spirals because that's what we know how to look for. So a couple of years ago, my team was like, well, could we look for other things? Could we look for things that are moving in some weird, unexpected way? And we've been training machine learning algorithms to do just that, to look for particles that don't move as a spiral, that will move in some new weird way. And it's funny because it's hard for computers to find that. But if I showed you one, if I found a collision that led to something which moved in a weird way, your eyes would be like, oh, that's something. What's that? Look at
Right.
that. That's weird. Our eyes are very, very good at seeing patterns, but I can't print out collisions every 24 nanoseconds and put them in front of my students and be like, find me the weird ones, right?
Right.
We have to use computers. That's because we need them because they're much more effective at this high speed, high volume data analysis. And so we're developing these algorithms to look for new weird non-spiral paths, and we're hoping when we run them on the data that they'll spit out something. Be like, hey, Daniel, look at this one. And then we'll get to see something exciting. So I'm working hard to try to sort of push the boundaries of what we can discover, but you never know what you're missing, right?
Is there a mathematical model that shows that the particle could move differently, or are you violating? Because you're a rogue, you're a maverick.
Yeah.
Is there a model that allows for that?
There are a few models that do predict that predict weird paths. For example, a magnetic monopole, a particle that has like just a north or just a south,
Yes.
not both. But my hope is that we find something that nobody predicted, right? I want to make the discovery that violates people's assumptions, that makes them go, what? That's impossible. That means we're going to have to tear up everything we knew. And like, yeah, that's the whole idea, right? So yeah, there are some predictions, but I'm not a fan of any of them. And I'm hoping we discover something that doesn't match to any predictions. That would be much more fun.
Have you ever found anything that maybe isn't a huge discovery, but made you go, whoa, I didn't see that coming? Have you been surprised? Anything in the data yet?
We had a moment in the data about 10 years ago when we thought we had a discovery. We were looking at events and we saw a bump, right? And a bump is how you make a discovery, a little pile of collisions that all look very, very similar. And it was in a place we didn't expect at all. And I had tingles. I was like, oh my gosh, have we done it? And we spent 6 months cross-checking it. Is there a mistake? Did we miscalculate something? Were we biasing ourselves somehow? And there was nothing we could do to make this bump go away. And I started to believe. I thought, oh my gosh. And this is big stuff, right? We could be discovering something that changes our understanding of the universe.
Oh, yes.
I started to think like, wow, this is, we're making history here. But the problem is that we look at a lot of data. And so when you look at, 10,000 different distributions of data, occasionally you're going to see one that looks weird. Just like if you try, flipping a coin 10 times and you do that 1,000 times, you're going to get some weird ones, right? Where you get lots and lots of heads.
Mm-hmm.
So we didn't know if we just like sifted through so many examples of data that we were just picking out the weirdest one or not. So we had to wait for more fresh data. So we ran the collider a couple more months and waited, and then the bump went away. So it was just a random fluctuation, unfortunately.
Now, something in my gut tells me a random fluctuation is not a thing.
Yeah, it's not a thing. It's just, it's everything that happens that comes out of the collider is random. And sometimes they pile up in a weird, unusual way. Just like sometimes, you flip a coin 4 or 5 times, you get 4 or 5 heads. It happens,
Sure.
right? And that's what happened this time. So it was exciting, but it wasn't anything. It was disappointing. And, we haven't discovered anything of the Large Hadron Collider since the Higgs boson. We saw the Higgs in 2012. We've been looking ever since, but it's exploration. Just like when NASA lands on Mars and sends a new rover, they don't know, are we going to find, something weird under a rock, or is it just going to be dust and rubble? It's exploration.
Right.
We're pushing those horizons, and I wish we had like 50 new particles to talk about that we discovered, but nothing so far.
So all of this is really about looking for accidents. And you have a great story, the Becquerel story, if you wouldn't mind telling it. It's so interesting. Is that the and maybe I'm getting his name wrong, the uranium photo.
Oh, yeah, Becquerel.
Becquerel.
Yeah. Yeah, this is one of my favorite stories about discovery in physics because it shows you that you just have to be paying attention and you don't know what the universe is going to reveal to you. Becquerel was in the late 1800s, and he was playing with uranium salts. And at the time, nobody knew what uranium was. They didn't realize what it was doing. It was something they put in glass to make it have cool colors. I'm like, that's cool. And he had a theory about uranium. He thought that if you put it in the sunlight, that it was going to absorb energy from the sun, and that then it was going to emit that energy, and you could see it on radioactive plates. So he had this whole experiment planned where he was going to put it out in the sun in Paris, and then put it next to radioactive plates, and he'd see the emission from the uranium salts. But it was cloudy in Paris.
What?
And so he didn't get to do his experiment. He put the uranium salts in a drawer with the radioactive plates and left for the weekend. And when he came back, for reasons I never understood, he was like, let's develop these plates and see what's on them. He didn't do the experiment he planned. He did some other thing he never expected to reveal anything. And what he saw is, the uranium salts are emitting. They left a shadow on the photographic plates. huge surprise to him. He was not expecting the uranium to emit without the sunlight.
Right.
And only because it was cloudy in Paris that weekend did he do this and discover radiation from uranium onto these plates. And then he deduced, oh, there's something coming out of this uranium. And, that's a happy accident. He discovered, I think, actually just a few days before somebody in England made a similar discovery. And he went from doing the experiment to analyzing the data to publishing it to, later winning the Nobel Prize.
Right.
But the whole exciting period was like a week long. He just barely scooped his English rival. So an amazing discovery. And to me, it's amazing because that could have been discovered earlier.
Sure.
Right. That kicked off our whole understanding of quantum mechanics. After that, you have the Curies and their exploration of radium, and understanding the atomic structure, which led to all sorts of radical new understanding of the nature of the universe. But he could have done that 20 years earlier, 30 years earlier, right?
100 even.
100 years earlier, and that would have changed the whole course of human history and our understanding of the nature of reality. And that tells you that a lot of the ways that we discover the universe are based on happenstance. Who happened to be in the right place at the right time and had the right idea, or were paying attention at the right moment. There's often these times when you discover something and then you think, wait a second, if that's true, couldn't we have discovered this earlier? And then you go back and you find the original data. You're like, oh yeah, look, there it is. There's the data. They just didn't realize it, For example, Galileo discovered Neptune and he didn't even know it. And you can go back and look in his logbooks and there is Neptune in his beautiful drawings with his own handwriting. Like, oh, that's Neptune. He should have noticed.
Right.
But it took hundreds of years before other people figured out Neptune was there and it was a thing. And that tells you that probably right now there is enough data, there's evidence for some crazy new discovery we haven't made yet in experiments we've already done. We just haven't figured it out yet. And in 100 years, somebody's going to look back and be like, Daniel, you could have won a Nobel Prize
right.
if you had understood what you had, right? But it's hard when you're standing at the forefront of human ignorance to know, where do I go? Where do I look? How do I figure this out? It's easy when you look back at the history of science and be like, oh, A, B, C, D, E. Because we tend to linearize it. We tend to think of the progression from where we were to where we are as a single path. But science is constantly branching and exploring. And we later pick the one path that brought us to this understanding. But it's filled with scientists going the wrong direction and playing around with stuff, and nobody knows who's going to be the one to hit the jackpot, right?
So what do things look like today? We have to play alternate history. Let's say that happened 100 years earlier.
Yeah.
What do Einstein and Bohr and Heisenberg and so that's 100 years ahead.
Yeah.
Where would we be now? What would they have been working on?
Yeah. I wish I knew. The easiest thing to say is that our understanding of the quantum realm would be 100 years further advanced.
That'd be nice.
That's incredible. I'd love to leap forward 100 years. But much more importantly, it would mean that generation of thinkers, Einstein and those guys, they would have grown up in a quantum world. So when Einstein was learning science and when he was, becoming a physicist, he lived in a classical world, right? Things were deterministic. Particles had trajectories. There was a location and a velocity to everything. That's the way he thought. So his theory of general relativity is a classical one in that sense. This classical is a funny word because sometimes we mean it to say original. And so he overthrew Newton, which is sort of classical gravity. But his theory is classical in a quantum sense, in that it insists that everything has a location and a time. And that's the challenge for us now, is to bring his gravity together with quantum mechanics. But imagine if he had grown up in a quantum world where thinking in quantum mechanics was not a new thing.
Right.
Maybe he was fluent in quantum mechanics. Would he have developed general relativity? Would he have built a classical theory of gravity? Or would he have already built a quantum theory of gravity? Maybe the whole reason we're at this impasse is because we have these two different thrusts. Einstein gives us relativity, and Bohr and Schrödinger give us quantum mechanics, and they started from different places, and we can't reconcile them. Maybe if Einstein had been, quantum Einstein, he would have taken a different path and developed a different theory of relativity or gravity, which was quantum compatible, right? So this whole 100 years of frustration we've had trying to bring these things together, maybe we could have avoided that if 100 years before Becquerel, somebody had left uranium salts on a photographic plate.
Yes.
That's all it would take.
That leads me to something I really wanted to talk to you about. Could we talk Kaluza-Klein a little bit and
Sure.
Rendell syndrome, that sort of thing?
Sure, yeah.
Boy, and you're working on Atlas. So Atlas has been looking for gravitons, right?
Mm-hmm, absolutely.
Without success.
Without success, yeah.
And looking, I think RS1 says there are 3 ways to prove gravitons exist, the particles exist, and we're 0 for 3, right?
Yeah.
Is the experiment wrong? Do we need more energy? Are they even there? Are they in? Is RS1 fifth dimension? Are they out there in compactified space? Maybe,
Yeah.
as Klein would have said.
Yes, so we can't see everything, right? The collider is limited.
Mhm.
Some things are too rare. Some things are too massive, right? We have a certain amount of energy in our collision. So we can make something on nature's menu if it has mass of a certain amount or below it. To go bigger, to go above that on the menu, you need a bigger collider, more energy. So we know that gravitons are not anywhere that we could have seen them, which means they're not below a certain mass or we would have seen them, and they're not above a certain rarity or we would have made them and seen them. So we can rule out low mass, very common, very high production gravitons. We can't rule out gravitons that are really, really rare or gravitons that are really, really massive. And so if the universe is like 5 or 7 dimensions, there are definitely configurations where there could be gravitons and we couldn't see them because our experiment is limited. So
Right.
we can't see everything. And that's frustrating. And that's why, I want to build a bigger collider and I want more space telescopes and I want all of this stuff because it's frustrating to be limited in that way. But yeah, we haven't seen them so far, and that's too bad. It would be nicer if the universe was easier on us and had a bunch of discoveries waiting for us just past the threshold, but it didn't play so nicely.
So I have a question that it maybe it's stupid, but it bothers me. But before I ask it, could you just catch everybody up in whatever terms you want what the hierarchy problem even is?
Yeah, so the hierarchy problem is one of those puzzles that tells us there's probably something that we're missing. It's a scenario where our math requires a big coincidence to work. And anytime there's a coincidence, it makes you wonder, like, is there a simpler explanation? And the hierarchy problem essentially says that the Higgs boson, the thing we discovered like 10 years ago, should be really, really massive. Because if you calculate how massive the Higgs boson should be, you have to add a bunch of terms and then you subtract a bunch of terms. And those are really big numbers because they depend on the Planck scale, like the power of the universe. And it seems very unlikely to add up a bunch of big numbers and then subtract away a bunch of big numbers and have them like almost perfectly cancel out. So the Higgs mass is really, really light compared to like the Planck scale. It's like 125 times the mass of a proton. Whereas the Planck scale is up at like, 10, 15, 20 orders of magnitude higher. The scale at which like quantum gravity effects turn on. And so it's weird that the Higgs mass is so small, that all these really big numbers somehow cancel out to give you a small number.
And is this also connected to the 4 fundamental forces, strong, weak, electromagnetism, and then gravity? Is this the same problem?
Yeah, the same problem.
Okay.
We seem to live in a universe where, we seem to live in a universe where gravity is really, really weak and everything else is much more powerful.
Right.
That same separation, right? It's the
Right.
same problem. And why are these things so separated? And so people wonder, like, well, is there a reason? Is there like an explanation? It's sort of like if you look at a coin and you say, and you don't know that there's 2 sides of the same coin. Somebody shows you heads, someone shows you tails, and you're like, it's weird. They have the same shape and the same size. It's a simple explanation is, they're 2 sides of the same coin, right? It's just one thing, not 2 separate things that happen to overlap, that happen to have the same size. So we're wondering if the hierarchy problem has a similar explanation. Like, yes, we add up a bunch of big numbers and then we subtract up a bunch of big numbers. It's interesting that they match almost perfectly. Maybe there's an explanation there. Maybe they're just 2 sides of the same coin, and that's a simpler explanation. So far, all of our explanations for that have failed.
Mm-hmm.
Like our favorite explanation is called supersymmetry, and it says just that all these numbers have to match all those numbers because there's a symmetry. The universe demands it. They're two sides of the same coin.
Now, I hate to do this to you, but you have to explain a little bit supersymmetry, duality, that sort of thing,
Yeah.
just to catch us up.
Sure. And so all the numbers that make the Higgs heavier come from its interactions with one kind of particle called bosons. And all the interactions that make the Higgs lighter come from its interactions with fermions. So there's two kinds of particles in the universe, bosons and fermions. We're made of fermions. Bosons are the particles that transmit energy, like photons and the W and the Z and the gluons and all this kind of stuff. And so those are two very different kind of particles. Like photons and W's and Z's don't match up with the fermions, the electrons, and muons, quarks, and this kind of stuff. So how do you make those things match up? How do you make it so these numbers all cancel those numbers? Well, you just say, well, for every fermion, there's a new boson we never seen before, and those two numbers match perfectly. And for every boson, there's a new fermion we've never seen before, and those two numbers match perfectly. So the ugly part is you have to double the number of particles. If say every particle has some partner out there we've never seen before, and their contributions to the Higgs mass exactly cancel, or almost exactly cancel. And that's why the Higgs has a low mass, because you have the pluses and the minuses and they balance perfectly. That's cool. And it's exciting because it means, wow, there's so many particles to discover.
Right.
And this is like 25 years ago, people thought, okay, there must be particles out there. It's beautiful. Also, the theorists love this idea.
Sure.
Because it's a fun playground. There's so many new particles to play with. And there's a beauty to it, right? There's an elegance to say, oh, this is only half of the story. We're missing half of the story. And there's history there. There's lots of times in physics when we've had a similar situation and it's worked out, like antiparticles. Oh, it turns out we're made of one kind of matter. That's just half of a symmetric thing the universe can do.
Sure.
The universe can also do this antimatter thing. Whoa, that's crazy, right? Or, oh, we have electrons. There's another version of electrons called muons and another version called taus. And that exists through every kind of fermion. So it's not just like wild speculation to imagine the universe has these structures and these symmetries and these patterns for us to discover. It was a good idea. And it was worth exploring. There was a lot of hype about it. A lot of people made overly strong bets about how we were going to discover it, and we didn't find it. It's just, it's not there. We looked for it, it's not there. If it's there, then it's very, very massive. In order for us to not have seen it, these particles would have to be really, really heavy. And that unfortunately breaks the beautiful part of supersymmetry. In order for these numbers to cancel out, the masses have to be basically equal. So supersymmetry could still be the law of the land. It could be the way the universe works, but it's really hard for it to actually solve the problem it was created to solve anymore.
Right.
And it's also the target of a lot of, I think, not well-informed criticism, because it was a fun playground for people. People developed whole research programs exploring supersymmetry, and certainly there were a few guys out there making broad claims that they shouldn't have made, and clickbait, whatever. We're definitely going to discover it, I guarantee it, or whatever. But that's not the mainstream view. Everybody always knew, hey, this is an idea. There were always other ideas, other possible explanations for the hierarchy model, and the experimentalists certainly never believed we were definitely going to discover it. We thought, hey, this is one thing we should look for. We should also look for the other things, and we should be open to new things we didn't expect, right? It's a broad field, lots of people investigating stuff. So supersymmetry these days is a bit of a, butt of the joke. People laugh about it. Ha, 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 you thought it was going to be real. But, it was a good faith explanation for a big mystery, a big question we had about the universe, which remains unanswered. We still don't know. Why is the Higgs boson so low mass? Why is gravity so much weaker than the other forces? It's not something we understand. And it could just be, hey, that's just the way it is. Could be no good explanation.
I need to ask my stupid question, and I'm sorry for it. But it might connect to later. So gravity's I don't know the numbers, 10 to the negative 35th or something like that against electromagnetism.
Yeah.
So we've got RS1, we've got the bulk, extra dimensions, space compactifies exponentially. Gravity originates from deep within there. I guess the Planck brain would be that endpoint. and gravity is super strong there, and by the time it gets to us, it's exhausted and weak.
Yeah.
What if there's an alien living, you have to do it, an alien living out there in the bulk,
Okay.
and they have a hierarchy problem. And I know that electromagnetism doesn't reach the bulk, but their gravities matches all their forces, and then they have this issue with there's something out much lower we don't understand, and it's a reverse hierarchy problem. Could that be a thing?
Yeah, absolutely. Yeah, aliens could have started from a different part of this whole big puzzle,
Right.
right? And an amazing fantasy is that they show up, they understand part of the universe, we understand another part, and then it's like chocolate and peanut butter, you know?
Yes.
Like we help each other out. Like,
Yes.
wow, that would be a great day. But, you know, in that scenario, aliens are living in like 5-dimensional world, and we're living in a 3-dimensional subworld. That would be very challenging to communicate. You know,
Yes.
beings that don't share our space, because we'd only be able to interact with like a slice of them, and they might not even be aware of us. So that would be really challenging from the point of view of like, hey, let's get out the chalkboard and talk about how these things work.
That was a perfect setup for our transition. We'll take a quick break and come back with the physics about our universe. Maybe the problem isn't our tools. Maybe the problem is us.
Yeah.
See you in a minute. So I heard you say, is the Higgs real when nobody's looking? I thought that was so funny. Can you retell the story and kind of tell us, why is Higgs important? Everyone knows what God particle, Higgs boson, everyone's heard of that. Good luck trying to explain it. You know, we don't know what that is or why it's important.
Right.
And that statement, when nobody's looking, that's wild.
Yeah. Yeah, so, you know, Higgs boson, a huge advance in particle physics. We discovered it in 2012. It was predicted 50 years earlier. And I love this story because it shows you the power of mathematics. Like, this was predicted based just on mathematical symmetry. You know, Peter Higgs is looking at the way the forces are, and he's wondering, like, well, look, electromagnetism is so similar to the weak force, but also very, very different. Like, why, if the structures are mathematically so similar, why does the photon have no mass? It could travel at light speed. And the W and the Z boson, really massive, very slow, very short range. Why is there a difference here? Why is the symmetry broken? And he was looking for a way for that symmetry to break. And like, what would require that to happen? And he said, well, you know, this actually would all work out perfectly if there was one more particle out there, one more field. And so you add that one piece, and suddenly everything makes sense. And that's cool, but it's a math game, right? It says, well, look, the math is nicer in this scenario, but is it real, was the question. And it's another example of like math leading us to discoveries, because it turns out it is real. It is how the universe keeps the photon from getting mass and getting the W and the Z to have mass. And that's incredible, because it tells you that like there's real mathematics at the heart of the universe, or, you know, it supports that argument. I can also make the other argument.
We're going to talk about it.
Yeah, but you know, what is the Higgs boson in the end? It's the thing that tells you that the particles we see are not the universe's fundamental particles. Like, when you look at an electron, when we measure an electron in the lab, what are we interacting with? What are we measuring? It's not just a pure electron. It's an electron bound up with Higgs bosons.
Okay.
Because an electron just moving through the universe would have no mass and would move at light speed, just like a photon does. But in a universe with a Higgs boson in it, it can't do that. Every step along the way, there's a Higgs field that's interacting with that electron. You know, it's like you trying to walk through a crowd of people, and they're all like, AJ, come, stop, talk to me, right? The same way, you know, we say that photons, when they move through a material, don't move at the speed of light.
Right.
Right? It's a little bit of a sleight of hand, because there's no time at which like there's a photon moving slower than the speed of light. It's an effective description. We say light is moving through the material as if it was moving slower than the speed of light. What's really happening is, you know, it's being absorbed and emitted and absorbed and emitted. It's interacting with the material. And so that changes effectively how a photon moves. There's no scenario in which the photon is actually moving slower than the speed of light. The same way an electron moving through the universe it would move at light speed and have no mass, but it interacts with the Higgs boson. And so we step back and we say, well, and a real electron, the thing we measure in the laboratory, is this electron that's interacting with the Higgs. It's an effective description. And so like a pure electron is this theoretical thing we never see. The real electron is actually this like buzzing interplay between two fields, the electron field and the Higgs field, which are very tightly coupled. So that's why electrons that we measure have mass. They don't really have mass in a pure sense. But the electron we interact with that we see in the laboratory that is used to build up me and you is this effective description. And what's really happening is this an electron field and a Higgs field tightly bound together. And so that explains why electrons have mass and why W's and Z's have mass. And that's what was important about the Higgs boson. But it's part of our model. It's our explanation for what we see out there in the universe. It's powerful because it describes future experiments. It describes what we see. It accommodates the universe. The question, though, is the Higgs boson real? That's a different question. That asks, is it the only way to describe the universe? Is it there when nobody's looking?
Ooh. What do you mean by that?
I mean,
this is not a wave function collapse argument, is it?
I mean, is the Higgs boson the map or is it the territory? When we describe what's going to happen out there, we use the Higgs boson. When the universe decides what to do, what's going to happen in the universe, is it using the Higgs boson? Or is there something else going on in the universe's true description of reality? Right? Is this our effective description that works really, really well? Or is it reality itself, beyond our ability to probe it and to think about it and ask questions? And this is a hard question to grapple with because it's not a science question. It's a philosophy question. I mean, is the Higgs boson real beyond our ability to test it, beyond our ability to do experiments? Because obviously the experiments match up with the theory.
Sure.
So scientifically, yes, it's part of our theory. It works. That's all good. I mean, is it there beyond that sense, in some deeper philosophical sense that you can't probe with experiments? But a more concrete way to ask that question is like, well, are there aliens out there doing science, building up their own explanation from the universe? Do they have a Higgs boson in their theory? Or have they found some other way to describe the same set of phenomena that they observe in their particle colliders, right? Is there an alien Higgs, eating haggis and doing all that stuff? Or is there not? Are there possibly other explanations? Because if there are, that means that our explanation isn't necessarily true. It could just be a map. It's not necessarily the fundamental reality.
So doesn't there have to be more because of dark matter and dark energy? So, because we don't know what that is, right? That's the placeholder.
Yeah.
Does that tie into Higgs? Is that maybe it's found in there somewhere? Maybe the aliens don't know what a Higgs is, but their dark matter energy is some other field.
Yeah. Well, a lot of really fascinating ideas there. It's true that we don't know what dark matter is, and we can't explain it. We don't know if it's made out of particles and what those particles are, et cetera, et cetera. That doesn't invalidate what we've learned about the universe, right? Every experiment we've done about atoms, our theory there works. And, it might not be fundamentally true. It might be one of many options, but that doesn't make it wrong. It means it might have the wrong context. It means that, the way Newton's theory worked for all the experiments they could do in their day, but, it wasn't the true story of the universe. In a broader context, Einstein's description is better, though who knows if Einstein is right. We may one day replace our theory of Higgs with something else, right? And that doesn't mean that Higgs was wrong. It just means that, it works under these circumstances. But when you replace it with something else, you also sometimes get to replace like the backdrop, the story about what's happening. Like think about what happens when you replace Newton with Einstein. You don't just get better predictions for Mercury and details about high-speed stuff. You tell a different story about gravity.
That's true.
Right? What happens when somebody jumps off a building? Newton says there's an acceleration, right? Gravity is a force. There's an acceleration of the person who's coming down to Earth. Einstein says, no. Person who jumps off a building experiences no acceleration. And he's kind of right, because if you took a scale with you and you jumped off a building and you put that scale under your feet, what would you measure? Nothing. Right?
Nothing.
Zero. That scale is an accelerometer.
Right.
It would measure zero. You feel no acceleration as you jump off a building. Why does it then seem like you're accelerating? Because the Earth is accelerating upwards towards you. So Einstein says you measure an acceleration because you, on the surface of the Earth, are in an accelerating frame. So we can dig into that more if you like, but the point is, you don't just replace Newton with Einstein, you tell a different story about reality. And so it's possible someday in the future we have a different theory of particles that doesn't include the Higgs, and we're telling a different story. The story I told you about electrons moving through the universe with Higgses and whatever, somebody on a future podcast could be telling a very different story about reality. So absolutely. And dark matter could be the key. You know, one thing we don't know about dark matter is, where does it get its mass? The electron gets its mass from the Higgs, right? But anything that gets its mass from the Higgs has to have a weak interaction, has to interact via the weak force. And so far, it seems like dark matter doesn't feel the weak force, which means it probably does not get its mass from the Higgs.
Right.
Which means, is there a dark Higgs? Is there another particle that gives mass to dark matter? Maybe. And, you know, dark matter, there's more dark matter than normal matter.
Right.
And so if there's a dark Higgs, then it's the dominant way you get mass in the universe. And our Higgs is just like a little bit of the story.
Right.
And so that could really help us understand like the bigger picture, how particles get mass and the whole context. So, you know, I don't want people to go away thinking, oh, our theory of the universe is wrong. It describes what we've seen and it works really, really well. But philosophically, we have no proof that it's the only description, the unique description, and we couldn't one day replace it with something better and deeper that works in a broader context to describe experiments we haven't done yet.
What's your gut tell you about dark matter?
My gut tells me that it's alien to us, that it's something we have not even considered. You know, the idea that dark matter is a particle, it's a fine starting place. Look, everything we've ever seen is a particle. Why shouldn't dark matter be a particle?
Sure.
All right, we can start there, but I wouldn't bet on that because everything we've ever seen is a tiny slice of the universe. It's like, you know, you've been studying an elephant's tail for 1,000 years and somebody says, oh, there's more to the elephant. Are you going to say, oh, the rest of the elephant is probably made out of tails? Like, no, it's not. This is an opportunity to say, oh, the whole context of my understanding is wrong. I need to like zoom out and think about other ways of things can come together. This is an opportunity for a revolution in physics. So it's fine to start there and to say maybe dark matter is a particle and maybe it's just one particle. We should look for that. It's worth doing. But to me, the most likely thing is that it's something we can't even imagine. It's something that's not a particle. It's another kind of matter altogether. Right? Why should the whole universe follow the pattern of this tiny little slice of the universe that's made out of atoms? That's just 5% of what the universe is. More likely, it's something very, very different.
Why isn't philosophy more tightly coupled with physics? I don't understand that because inevitably you have to talk about philosophy, don't you? I mean, I know you do, but most physicists don't even want to go there.
It's a great question. I think physics and philosophy are deeply intertwined, right? Philosophy is why physics is interesting. Imagine the day we get the answer to my question. Okay, we found the fundamental nature of the universe. It's these two things. And everything bubbles out of that. We can explain everything, economics, string theory, pies, whatever, kittens, from these two things. Then we'll have the philosophy question. Why these two things?
Right.
What does that mean about the universe when we've laid it bare and we've seen its fundamental nature? That's why it's interesting, because of the philosophical questions. So they drive all of our science. But most physicists are not interested in or not educated about, I'm not sure which, philosophy. And I think that historically it's been sort of dismissed. You know, you have like famous folks like Feynman saying physicists need philosophers the way like birds need ornithologists or something. And it's a clever quote, but I don't honestly even get it, because I think birds could use ornithologists, like
Sure.
who doesn't want to understand the context of what you're doing and why it's important. So I think a lot of physicists, they're more mathy people. They're less humanities, and philosophy is squishier. It's not so mathematical. You can argue about something in philosophy for literally 1,000 years, make no progress, right? That's frustrating. And you could also never know who's right. Right? Some of these questions in philosophy, there's no experiment you could do to settle them. There's no formula that tells you who's right. One of the reasons I got into physics is I really loved the concrete nature of it. Like you do a problem, there's an answer, right? It's right or it's wrong. Not like, I didn't like your essay, I didn't like your story, it didn't really stick with me. I mean, this, you're in entertainment. Like, it's fuzzy. Like, is this novel good? Is my screenplay good? Is it bad? And nobody really knows, right?
Mine are always bad, but
right? You can't really tell, but you can tell when your physics is right.
yes.
You can tell when your experiment is telling you something new, and that's satisfying and concrete and objective. I think a lot of physicists latch onto that, and philosophy is hard to deal with from that perspective. And I think that a lot of physicists have strong opinions about philosophy, while at the same time not taking philosophy seriously.
Didn't they get into physics because of philosophy and didn't even know it?
Yeah, maybe. And
Because they're asking questions.
they're asking questions, and they think things about philosophical questions. Like if you walk around CERN and you ask people, you think the Higgs is real? Of course it's real. What are you talking about? We discovered it right here. Like, there's a Nobel Prize for it. Are you crazy? Like, what are you smoking, and where can we get some?
Right.
Right? Because they think, like, we've discovered it. It's part of our model. We've proven that our model describes the universe. Therefore, it must be part of reality. And that leap, that step to say, it's not just something we can predict. It's not just part of our model. It's there. It was there before us, right? It's aliens will see it too. These are not scientific statements. They're philosophical statements.
They are.
And people have strong opinions about it. But they also think philosophy is, a foolish waste of time. So one of the reasons I wrote my book is not just to educate people about these interesting philosophical questions, but other physicists that I hope will read it and be like, oh, these are interesting questions by smart people who have thought about it for hundreds of years. Maybe I should, think about the broader context.
I suspect that more physicists agree with you than admit it. What do you think?
Could be. And I think the things are changing.
Okay.
We've seen a sea change from folks thinking like questions at the heart of physics, like quantum foundations. Does the wave function collapse? What does that even mean? 50 years ago, people said, shut up and calculate, right?
Right.
Who cares? Whatever. The calculations work. Why are you bothering me with these philosophical questions? That was the prevailing wisdom. But, now we have a lot of progress in quantum foundations, people working on many worlds and Bohmian mechanics and all sorts of stuff. And I think that's being respected now. And so I'm glad to see an opening of the field, people willing to dive into these philosophical questions at the heart of physics. And I hope to see more interaction between physics and philosophy departments. At UC Irvine, we have an amazing department of logic and philosophy of science, staffed with guys who have PhDs in physics. Staffed with guys and girls who have PhDs in physics. They know what they're talking about.
Sure.
They're really smart folks with really interesting ideas.
So a good response from a physicist on Higgs is, well, the math works. So can we do physics without math?
Can we do physics without math? Yeah, I don't know. On one hand, you would think, gosh, you got to have math to do physics. It's like asking, can Shakespeare write without language, without English? It is the language of our science. And the example of Higgs is an example of math leading us to a discovery, right? Not just being useful, not just expressing our answers, but like pointing us in the right way. Follow your mathematical instincts, and the universe is mathematical, so you will make discoveries. And there's so many examples of that, right? There's Maxwell, for example.
Mm-hmm.
He's putting together Gauss's law and Ampere's law, and he's using symmetries. He's like, let's figure out how we can write these things the same way. And that works, but he notices that there's a piece missing. He's like, this would be more symmetric. These equations would balance better if there was another piece, which we now call displacement current. He didn't know it existed. He just wrote it in there because the math told him to. He's like, ooh, I can't resist adding this term. And then went out and discovered it's real. It's part of the universe. So again, the mathematics, the desire for symmetry, for mathematical structure, leads us to discoveries. And, I think it's underappreciated how well our theories work. And I had this moment when I was an undergrad learning quantum mechanics, when I saw a calculation done in quantum field theory that predicted an experimental measurement to like 9 decimal places. You should measure this thing and it'll be 0.4721, 9 decimal places. Then they go out, they do the experiment, they measure this thing, and they get it right to 9 decimal places. And I saw that and I thought, oh my gosh, the universe is mathematical. Right?
Of course.
How could it not be?
Of
It's
course.
so precise.
Yes.
Right? And I took that leap to say, it's not just the map, it is the territory, because it's so bang on. And if it was just the map, it'd be fuzzy, right? And how could it be this precise and not be the way the universe is doing its calculation? I'm not a religious person, but that was almost a spiritual moment for me where I thought, I'm seeing the face of the universe.
Of
right?
course.
Very powerful. So there's a lot of good reasons to think the universe is mathematical. We have to have math to do science. When aliens arrive, they're going to be doing mathematical science, right? Sure. But there are also pretty good arguments on the other side, right?
Yep.
And the more you dig into it, the more you realize, we don't really know. I mean, I said, okay, everything is very, very precise. And that's true, but it's never exact. These calculations we do that involve 9 decimal places, they take a huge number of terms to calculate. We do these perturbation series. So we do a calculation and we do one part of it. We don't expect to capture everything, and it gets it mostly right. And then we want it to be more precise, we add more terms. These are the Feynman diagrams, and they get more and more complicated. And the more complicated a Feynman diagram, the smaller its contribution is to your calculation. So you can just do one Feynman diagram and get it mostly right. You can add more and get it more correct. It's a series, and it converges to a number. You never get there. You never bang on. Our calculations are always approximate. They're shockingly accurate when you push them, but they're never the description of reality itself. There always is a fuzz there. You can never get to perfection. So it takes a little bit of the shine off of the universe is doing this also, because it feels like, the universe has to eventually make a decision about what happens to this electron or that electron. It can't do an infinite calculation, right, in finite time. And then you start to think about the philosophy of the mathematics, and we also have a great philosophy of mathematics group at Irvine, and to think about what are these things that we're dealing with? Do you really need these numbers? And a central part of all of our calculations in physics are something we call fields, right? Gravitational field, electromagnetic field. And they're actually at the heart of our explanation of the universe itself, right? These days we think about particles, but we don't think of them as the fundamental element of the universe. We think of them as ripples in fields. And fields are the foundation. So we don't know if this is the end story, but the current foundational picture of the universe is space-time with a bunch of fields layered on top of it, right? Electrons, ripples in electron fields, muons, ripples in muon fields. Cool. And if you ask a physicist, are fields real? They'll say, yeah, of course. I mean, they're at the foundation of our calculation. The problem is nobody's ever seen a field, right? You've seen a field push on something. You've seen a field bend a particle, those spirals we were talking about, where charged particles moving through magnetic fields. You're not seeing the field. You're seeing the effect of the field. So some people think, maybe fields are not real. Maybe they're just a calculational tool. They're like an intermediate step in the calculation. Like if you want to calculate the force of gravity on something and you're using Newtonian gravity, you can just calculate all the forces at all times. Or you could say, look, I have this thing, it has a mass, I'm going to calculate the gravitational field. That's a helpful first step so that anything that comes near it, I know already what the forces are going to be. It's like get you halfway. And maybe the fields are just a calculational tool, right? Then maybe they're just in our minds. They're like a helpful way to organize our calculations, not something that's out there in the universe. So there's a philosopher out there, his name, ironically, Hartree Field, and he wrote a book called Science Without Numbers. And what does that mean? Science without numbers? Like, what are you talking about? And his basic premise is fields aren't real.
They're not real.
They're not real. They don't exist. And he goes further than that. He says numbers aren't real.
What?
What? What does that even mean? So he's saying that the way that fields are a calculational tool, they're an intermediate step, that the number line itself is that way. He's not saying you can't have like more of something or less of something. This is bigger than that. But it's an abstraction to say 2 is a thing, 3 is a thing, right? We could say this has more than that, this is closer than that. But to construct a number line is to create an abstraction which is a useful intermediate in to talk about these things. Because instead of saying this is bigger than that, you can say this one's 2 and that one's 3. And then later I can compare them. So it's a halfway mark to our calculation. So he built a whole theory of gravity without fields, without numbers, just based on like closer, further, nearer. And, this book, I read it. It's not easy. It's a brain twister to try to think about physics without any numbers at all. And it's not a pretty theory, right? It's not very useful. It's not like the way anybody should do physics.
It's pretty mind-blowing, though.
It's mind-blowing in the consequences because it means you don't need fields. You don't even need numbers.
Is it true that fields prove Newtonian gravity without numbers?
This book rederives Newtonian gravity without any numbers.
That's bananas.
Yeah, and it works, right?
And it works.
Just
based on relationships.
Just based on relationships. And it tells you that you don't need the fields, you don't need the numbers. Maybe they're just a convenience. It's not arguing that math is not useful, that it's not powerful.
It's just a tool. It's a shortcut.
It's a shortcut. The way that taking notes on something as you are thinking about it is helpful, right? Or organizing your desk, it makes you a more effective person or whatever. Keeping a calendar is useful. Well, not necessary. You could get by without it.
Sure.
And what that tells you is aliens, maybe they don't have the same mental shortcuts. If their minds work differently, maybe they came up with another halfway point for their calculations, another convenience, another way that reflects the way they think about the universe, which could be the same as ours or could be very, very alien, right?
Right.
And so that opens the door to thinking about how elements of our science could reflect our humanity instead of reality. And, back to the question, is the Higgs boson real? Well, I don't know if any of these fields are real. I don't know if anything that we've described out there has to be the way we think about it. Or it could just be that this is a way for us to express how our thoughts work, right? Maybe this lens we thought was focusing on the universe is also reflecting something of ourselves.
So if aliens arrive and their physics or their whatever they're doing, they're not using numbers, does that mean our number system, our tool, is in the way? Could we be limited by our own senses is what I'm kind of getting at.
Yeah, it could be, right? It could be that it expresses the way that our minds work, but it could also be limiting, right? It could be that it shunts us into certain ways of thinking about the universe. It closes doors that we imagine shouldn't ever be opened or we don't even realize are there because of the way we're thinking. And, I suspect in that scenario that human minds are very, very diverse. Aliens show up, they have another way of thinking. It's very confusing at first, but then some parts of us, some few, maybe neurodiverse elements of humanity are like, actually, that makes more sense to me. I never really got what you guys were talking about.
Right.
Your math, human math never really clicked. This alien math is my stuff, and then they're off to the races with alien math and thinking about the universe. That would be so much fun. Absolutely. I think that the way that we think and experience the universe must somehow limit the kind of ideas we consider, the way we express them, and also the answers that we will accept, the way that we are satisfied, right? When you give somebody an explanation, you wait until that moment when it clicks in their mind. They're like, oh, okay, I got it. I have a thing in my head now which satisfies my constraints. And that's personal, right? What it takes to make that click for everybody depends on how their minds work. And so if aliens have different kinds of minds, they might find our answers just like unsatisfactory and vice versa.
Sure.
Right? Say they show up and we're like, what is quantum gravity? And they tell us and we're like, that doesn't really make sense to me. Like, what are you talking about? Like,
Right.
no, I still have questions. That would be pretty disappointing.
It would be. Because if aliens show up, they've clearly solved, or at least most of it, quantum mechanics. Is it possible we're just not capable of understanding it? We're just not wired for it.
It's possible, right? We don't know, frankly, why we can understand so much. Like, our minds evolved in a very different scenario than we live in today, right? They evolved to keep us warm, to make friends,
Right.
to stay fed in a certain environment. And nobody knows for sure exactly why we developed intelligence and how it's useful. And there's great theories, and I'm not an expert in them. But I'm sure that like thinking about 11-dimensional space and doing like crazy integrals over those spaces was not essential for survival
No.
a few thousand years ago. Yet here we are doing crazy mathematics that are essential for understanding the universe. Why are we capable of that? What is it about that experience? What evolutionary bottleneck produced this mind which could solve that problem to survive and yet also had this capability? Nobody knows the answer to that. But it suggests that there may be a limit, right? Because our minds come out of some sort of structure of, the neurons. And again, I'm not a neurologist or anything, but we think that, evolution controls our intellectual capacity, and therefore we're a product of this intellectual evolution, and there should be a limit to it somehow. I mean, we see limits in other creatures. I love my dog. It's very smart. I'm impressed by it. It can learn. I will never explain general relativity to my dog, right? It's just,
Right.
You'd laugh at the idea, right? Of
Right.
course not, right? The dog could never understand that. So then why would we imagine that there are ideas out there, that are never beyond what we could think, right? That aliens might show up and they have bigger brains and they understand the universe and they explain it to us and we're just like, huh? Like the Ed Whittons among us,
Right.
could never grok it. It seems to me possible that the universe works in a way that is beyond our mental functioning, right? But there are tricks we could pull, but I don't think we have any guarantee that the universe has to operate in a way following mathematics that we can understand.
There's a theory, and it drifts into religion a little bit. Is not only we don't understand quantum mechanics now, but we're designed so that we can't ever learn it, because that would reveal too much to us. That we are locked in a certain box, and that is our limit, and you go no further.
Yeah, it's certainly possible that we can never understand quantum mechanics, that it's an example of something which just doesn't mesh with our intuition. I think that's something that most people don't appreciate enough, is how intuitive we demand our physics to be. Think about how we understand weird things. When we talk about gravitational waves, people often explain them in terms of ripples in space-time that have a certain frequency, so they describe them as a sound, right? The universe is chirping at us. Or even more simply, if you look at images from the James Webb Space Telescope, right? You're not seeing the images from the Space Telescope
No.
in the colors that it sees them. You're seeing them color shifted into the visible spectrum, right? Why do we do that? Because we understand the universe in certain terms in our minds, right? And when we see something weird, we need to translate it from the weirdness to something familiar.
Right.
And we demand that familiarity. And when we think about quantum mechanics, we're doing the same thing. We're saying, all right, this is something new and weird. Let me explain it in terms of a language of primitive ideas in my mind. Okay, is it kind of like a really small rock? Yeah, kind of. Okay, is it kind of like ripples in a pond? Yeah, kind of. You kind of actually need both of those, even though they conflict with each other. It doesn't really work. And the reason it doesn't really work is it's not something that aligns with anything in our primitive mental library, right? It doesn't line up with this. It doesn't line up with that. It's something new and weird. It's not simultaneously a particle and a wave. It's neither. It's something new that's somehow kind of captured by this and that. It's like you eat a new fruit and you're like, I'm sensing notes of cranberry. I'm sensing notes of an apple. It's not sometimes an apple and sometimes a cranberry. It's some new weird thing that's kind of reminiscent of things you're familiar with.
Yes.
And so we tend to have this language in our minds of ideas we know how to play with and talk about and think about, things that make sense to us. And I do think that that limits our capacity to explore the universe already, even without aliens coming and giving us crazy ideas. You know, quantum mechanics is already pushing us maybe to the edge of being able to understand that. We can use mathematics, we can use philosophy, we can talk about it, we can build our society based on understanding of quantum mechanics, but we may never like really truly grok it because of fundamental limits in the way our brains work. And I think that comes out of our intuitive experience, you know, the things you interact with when you were a child. I think it comes out of our senses, you know, the ways we see the universe, the tiny slice of the universe that we are actually able to perceive and interact with. It must shape the way that our minds work, and this primitive language of intuitive objects that we demand everything get translated into, which is terribly confining. I mean, it's very powerful, but it's also really confining.
I'm glad you mentioned that, because when you think about certain birds using cryptochromes in their eyes to entangle and see the magnetic field of the Earth, that's bananas.
It's incredible.
Oh, so it's possible there are senses that we just don't have them.
Certainly there are. We've discovered them, right? We know that there are senses out there. Like there are fish that can sense electric fields natively, right?
Yes.
What is that like? What is the experience of that, right?
They're doing radio communication essentially, no?
Yeah. Yeah, and that to me is frustrating because it suggests we could have had telepathy, right? We could sense electric fields. We could generate electric fields.
Sure.
Why can't we just think back and forth? Why do we have to go through this whole like lip flapping thing, right? Physics does not prevent telepathy. Like, in fact, it enables it. So I don't know why we didn't evolve telepathy. it's a big missed opportunity. But so certainly there are senses out there that we don't have that prevent us from interacting with the universe in a native way that aliens might have.
Right.
Maybe just they got lucky evolutionarily, or they evolved in a different environment that demanded those senses, right? And so they have these different senses. Or maybe, for example, aliens are microscopic. Here's a mind-blowing potential is, what if aliens can interact with quantum objects without collapsing them?
Wow.
Right? I mean, the reason that photons collapse when you experience them, if I shoot a photon at your eyeballs and I give it a probability to go to the left or to the right, you only see it in one.
Right.
Because your eyeball is a classical object. It's big, it's fat. It collapses that wave function. But if you were tiny, if you're microscopic, if you are a quantum objects can interact with other quantum objects. They get entangled, but there's no collapse. What if you could experience both branches of that wave function natively? You could just like, oh yeah, 60% this one, 40% that one, instead of being forced to choose. If you live in that world, you're a tiny microscopic alien that can interact quantum mechanically without collapsing stuff. What's your understanding of quantum mechanics? It's just mechanics.
It's just mechanics.
Right? It's just the way the universe works.
Right.
And you come to meet us, you probably don't even understand what we don't understand, you know? Like when I try to explain how to program the VCR to my grandfather, like, what's confusing about this? It makes perfect sense.
All of our
right?
grandfathers.
Like, where are you missing the story? I don't get it.
So many blinking 12
Yeah,
forever.
Exactly. And
Is there anything mathematically that prevents that? Because intuitively, that sounds like it could be a thing.
I think it could be a thing. There are limitations to how small you can be
Sure.
and still like have information and have it be not too noisy and develop intelligence.
Are there limitations? Because aren't we back to Planck again? What if there's not? We're only 5% there.
Yeah, we're only 5% there. Yeah, I think that's a possibility. I don't know. I'm not an expert in neuroscience. And, you know, I think when we're talking about aliens, we should imagine all sorts of crazy possibilities for how they could process and store information. And you could definitely do a lot of information processing, a lot smaller than we do it, especially if you're not using organic neurons. So yeah, and I'm not an expert in brains at all, but it seems to me like aliens could very likely have a different set of senses, a different kind of experience of the world. Our experience of the universe is not the only way to experience it. Another possibility is like, what if aliens are made of dark matter?
Yeah, I was just going
Right?
to ask you, what if they have
Yeah.
if they can see dark matter just with a sense that we don't understand, and maybe the sky's full of stuff that they can just see.
Yeah, absolutely. Because it could be that aliens, if they're made of our kind of matter, we hypothesize that dark matter might have a new kind of force that lets it interact with our kind of matter. We hope that it has that force. We have no evidence for it. We hope because that would let us discover it. If there is some sort of like interaction between dark matter and normal matter, not the weak force, not the strong force, not gravity, not electromagnetism, some new force.
Doesn't it have to interact with our stuff, because otherwise everything would fly apart? No.
It has to interact with our stuff via gravity.
Okay.
And you're right, that's what's holding galaxies together and shapes the large scale structure of the universe. Definitely interacts via gravity.
Okay.
But via gravity is very, very weak, right? So if there is dark matter out there and it only interacts gravity, there's basically no way we could discover if it's made of particles, because a dark matter particle that interacts only via gravity, undetectable. Gravity is way too weak, right? But if there's another force, and this is the big hope, that maybe there's some other force out there that lets normal matter interact with dark matter, and we could see dark matter winds interacting with us somehow. Well, if aliens can sense, that force, then maybe they could see dark matter natively, and to them it's not a big mystery, right? To them, they see the whole picture, and they went a very different path for their science, possibly. Or even weirder, if they're made of dark matter, right? If dark matter is some new kind of particle or new kinds of particles, and it has dark physics and dark chemistry, why couldn't it have dark biology? We're talking about 5% of the universe made of atoms has all this complexity in it. Now, the other 30% of the universe, why shouldn't it have complexity? Right? Why shouldn't it be made of many different kinds of things with complicated emergent phenomena? Maybe it's boring, maybe it's simple, but maybe it's very complex, and maybe there's life in there. In which case, aliens could be made of dark matter instead of normal matter. And wow, what a different way to experience the universe.
So I love that theory. I never considered it. But it also makes me wonder, we may not have the biological capability to understand how to create the device or the mechanism to ever see it. Because we don't, you can't find what you don't know what you're looking, you know what I mean? You don't know what
Yeah.
you're looking for.
Yeah.
Maybe we can't perceive it.
Yeah.
Is
It's possible, but I will always bet on humans to figure this stuff out. We've discovered dark matter even though it was hard. Like, it was not obvious, right? This is why it took so long
right.
to figure out that dark matter is even there. Now we have lots of very convincing evidence that something is there, some kind of matter. We don't know what it's made out of. We don't know how it works. Something is out there. Something is gravitating. And I think we'll figure it out. I don't know how, but I would hate to say that it's always going to be a mystery, because that undersells our children, our children's children, our future, that nobody will ever be smart enough. It's possible, of course, and I have to admit that it's possible, but I hope that's not the case. That would be very sad.
These are a lot of fascinating theories, and I have a concern that's shared by most of my audience, that there's some kind of institutional gatekeeping with these ideas, with I hate outside the box, I hate a cliche, but these kinds of new ways of thinking that you're talking about. Is there gatekeeping? Are there people saying we this is physics and that's that?
Well, I think there are structural issues with academia, and with science, things that encourage people to follow up on existing ideas. There's also structural things that encourage people to go out on a limb. There are Nobel Prizes for people who make crazy discoveries that overturn everything. There are lots of awards. There's recognition. Like, it's everybody's dream. It's the best thing you can do in your career is to discover something new that overturns, everything we ever thought. It's what everybody wants. But there is a structural pressure also that encourages people to follow up on existing ideas. So for sure. But there's no like sense in which scientists are getting together to say, let's shut down that idea, it's dangerous or something. Scientists are not so organized. There's no coherent group of us in a back room smoking cigars and deciding what we're going to publish. Science follows the data. Every example people bring up of like historical gatekeeping, Galileo or, plate tectonics or whatever, that's a story of data persuading the community of a new idea. That's actually a story of science doing it right. Galileo, for example, who was doing the gatekeeping there? It wasn't the scientists.
No,
it was the church.
It was
church. Political, right? Science responds to data. And I think anybody who says like, look, I have a crazy new idea. Why won't science pay attention to me? Like, well, you need data to back this stuff up. And that's where the argument is. And, it takes a while to convince scientists and the mainstream to change course. But I also think that there's wisdom in that. We don't want to like throw away everything we've built for the last few hundred years every time somebody publishes a new paper, right? You wouldn't change careers every time you hear about a new one. It takes some time to invest and explore, right? You don't burn down your house every time you see somebody else's house that looks cool and start afresh. So it should take a lot of data to change everybody's minds. It should take an overwhelming argument. And that's what happens. And you see that at play right now in science. Let's take, for example, our understanding of the early universe, right? We have this description we talked about earlier, the Big Bang, the universe expands. But there are problems with that, right? Mm-hmm. We measure the expansion of the universe today, we get a certain number. We go back to the very early universe and we calculate how much stuff there was, and we propagate that forward in time and say, well, how fast should the universe be expanding? We get a different number. So the early universe measurement of how fast the universe was expanding disagrees with the measurements we make today. It's called the Hubble tension. Big problem currently in cosmology.
Is that a large delta?
It's not a large delta,
okay,
but the measurements are both very precise. So it's significantly separate, even though it's like 8% different.
But doesn't that mean physics was 8% different?
We don't know, right? We have no current good understanding of this. And what you see playing out is people trying out new ideas. Maybe the universe's expansion is not the way we thought, or maybe there's a problem with this measurement, and people are poking at every aspect of this, coming up with, well, is there a new way we could measure this that doesn't make that assumption? Is there a new way we could model this that doesn't make that assumption? In real time, you're seeing science be open-minded, be accommodating, admit that we don't know everything, and stumbling around looking for an explanation that will fit the data. Somebody comes up with a model that fits the data, makes a prediction, and is verified. There's Nobel Prizes there, right? And also the history of dark energy, the whole discovery, the fact that the universe is expanding and that expansion is accelerating, that was a big surprise. Nobody expected that. That overturned generations of dogma, of narrative, right? But the evidence was overwhelming, and there were two separate groups that saw the same thing, and the evidence was indisputable, and so science pivots. And that's what happens. Science changes when you see the data. And so, I know there's frustration. There's people out there who have an idea and it's not getting enough attention. I have a screenplay I've written. It's not getting enough attention.
Nobody wants to read your screenplay.
I know.
I know. I hear you.
It's a common feeling that like your stuff is not getting enough attention. I feel the same way. Most of my grants that I submit to the U.S. government are rejected. Do I think that's a mistake? Yes, absolutely I do. I don't blame it, it on jealousy or gatekeeping or whatever. Like, it's a marketplace of ideas. It's an imperfect, absolutely, it's an imperfect marketplace. The same way that like there are probably great screenplays out there in drawers in Los Angeles that nobody's producing that would be incredible, right? I'm sure that's true.
There's great screenplays in drawers right here, Daniel.
Somebody should make your movie. It's imperfect, but it's gotten us pretty far. And I think the most important thing to remember is, people are operating in good faith. Scientists are just busy, curious people like you. There's no time to read everybody's theory. The same way that like Jerry Bruckheimer can't read every single screenplay, right? I actually do my best. Everybody who emails me their theory, I give them 30 minutes. I read the first piece. I give them some feedback. I think it's important for science to be responsive and to be accessible. I work at a public university. I'm paid by taxpayers. I should be responsive to the public. So, email me your theory. I'll give you my idea on it. A lot of people don't like what I have to say about their theory, but,
As long as it's honest.
yeah, absolutely. And almost every scientist out there is operating in good faith, doing their best to try to advance our understanding of the universe. So, is there gatekeeping? I think there's consensus. I think there's competing ideas. I think it mostly works well. I can't imagine a better system. What I do think is that we're operating under unfortunate constraints. Like, why is science conservative? Why do we have a consensus? Why do we not explore more ideas? Because frankly, funding is shrinking and research budgets are going down, 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 down. What happens when you shrink research budgets is people get more conservative. You have less money to like, hey, let's invest in Professor X's crazy idea, as well as, the mainstream ideas we've been working on for the last 50 years. We should definitely, balance existing ideas and crazy new explorations. Absolutely, we should do both. But when research budgets shrink, it's awkward to know how to manage those things. And that's what we're seeing. And so people tend to fund things they know are going to produce something useful on shorter and shorter timescales. And I think that's a mistake. I think we should fund more crazy ideas, more people trying weird things, more people saying, look, I don't know what this is going to do, but I have a hunch I want to go in this direction. I think a lot of historical great discoveries come out of that, just like blue sky craziness, give the nerds some cash and let them play.
Absolutely. And if you polled Americans, overwhelmingly, they would fund the sciences over defense. But you reminded me of something. So you're not getting a lot of grants, but there is one you got that's pretty cool. And you are a guy who likes crazy ideas. Can you tell me about how we can turn every cell phone on Earth into a cosmic ray detector?
Yeah. There's this great mystery in cosmic ray physics. Cosmic rays is a fancy name for just like particles coming at the Earth. You think of space as empty, but it's actually filled with particles, right? Very, very low density compared to like our atmosphere, but high-speed particles whizzing around. The sun.
That's where the government gets their 0-point energy, of course. Everyone knows that.
The sun is making all sorts of particles. Black holes emit particles, all sorts of stuff out there in space. And the amazing thing is that there are particles out there with such crazy high energy that nobody can explain it.
How high?
So the Large Hadron Collider can make collisions up to 10 to the 12 electron volts.
10 to the 12.
Yeah. 10 to the 12 electron volts. So that's like 10 to the 12. So that's like 1 trillion times the mass of a proton. No, sorry, it's
I'm trying to do it too.
GeV.
I have to let the physicist, he'll be faster.
So that's like 1,000 times the mass of a proton.
Okay.
And that's pretty impressive.
Mm-hmm.
But there are particles we've seen from space that are like 10 to the 9 times more energetic, right? So like 1 billion times more energy. And that's amazing. The universe has an accelerator that way, way outputs ours, right? It puts ours to shame.
What fraction of the speed of light would those be?
These things are no.
Oh, wow.
Like they are really redlining it.
Where are they coming from?
Speed. So some of them come from like the centers of galaxies or from really big stars or other stuff. But some of these things, we cannot explain it. Like there's nothing out there in the universe. You ask an astrophysicist, like, give me a particle of this energy, how do you do it? They're like, we don't know. Start from a supernova, whiz it around a black hole. Nobody knows how to get particles at this high energy, especially because the universe turns out to be opaque to these kinds of particles, meaning it likes to absorb them. So you shoot a particle out at this high energy, it shouldn't go very far. It interacts with the cosmic microwave background radiation, and it loses its energy. So not only is there something new out there that nobody understands, capable of making particles at super high energy, it's not very far away. And nobody knows what it is.
It's not very far away.
It's not very far away because these particles cannot go very far through the universe. So if we're seeing them here on Earth, and we're seeing them, then they can't come from like all the way across the universe. They have to be coming from our galaxy or one of the neighboring galaxies. They can't go any further than that. So they're in our cosmic neighborhood. The challenge is they're rare. We've seen like in decades of looking, we've seen a handful of these. So we can't even like say, where are they coming from in the sky? Are they all coming from the center of the galaxy? Are they all coming from this one planet that's orbiting that star? And this is like aliens shooting a message at us? We can't even do that kind of pointing because we have a handful of them. And the reason is that they're very hard to spot. They hit the top of the atmosphere and they create a big shower of particles. So one energetic particle turns into two with less energy, which turns into four, which eventually, by the time it hits the ground, is like 1 trillion particles.
1 trillion?
Oh, trillions, absolutely.
Wow.
And so you get this like wash of particles over the surface of the Earth. Like super high energy particle hits the atmosphere, then you get a big flash across the surface of the Earth. And so to see more of these things, you either need to build like really big detectors. They have these dedicated detectors they built like in South America and in a desert in Utah to see these things, but they cost like $100 million. Mm-hmm. So you can make those bigger if you had billions of dollars. Elon, call us. Or my idea was, look, why don't we piggyback on existing technology? Instead of spending money to build dedicated scientific instruments, is there something that's already out there that we're spending a lot of money on that could see these things? And so your phone is effectively a particle detector.
How does that work?
Well, it has a camera in it.
Sure.
Right? And what is a camera other than a particle detector? And these days, cameras are little CMOS chips. They're these little piece of silicon. And when a photon comes through, it liberates a bunch of particles and then it gets read out.
Yep.
If a muon goes through, same thing happens.
It does?
Absolutely. In fact, we use the same technology to detect particles at the Large Hadron Collider. Same silicon technology is used at the heart of every detector at the Large Hadron Collider.
Is that something that you would see in the photo on your phone?
Absolutely.
Like,
So,
oh, wow, I got a lot of muons today. Like,
if a muon goes through, it'll leave like a little white spot. Or if it comes through at an angle, it'll leave like a little track across a few particles, across a few pixels. And so, yes, you can absolutely see it. Mostly it's washed out because you have a lot of light. But if you put your phone down on the table so the camera's face down, it's not getting any photons. But if a muon goes through, it'll pick it up. So we had this idea a few years ago, about 10 years ago now, and I thought, I wonder if I can write an app which can scan the camera to look for muons while it's like on my table at night and see these things. So I spent Christmas writing my first app. Let's see if we can get this thing to work. Proof
Learning
of principle.
Lua?
Yeah, exactly. It was actually on Android, so it was mostly in Java.
nice.
And it works. You can see muons. So I thought, whoa, my phone.
You saw some?
Yes, I saw some.
How did that
Absolutely.
feel?
It was amazing, to see a signal emerge from the noise.
Did you
it's
hold?
really awesome.
You had to hold a family meeting because your wife is a scientist, right? Molecular biology.
Yeah, she does microbiome research. She understands like how the gut works and all the microbes in it.
Do you
Yeah.
guys ever fight about like whose science is more fundamental? just let her win.
Yeah, well, her science is definitely more useful. Yeah.
That's for now. So it worked. That's crazy to me.
So it works, and that's amazing because there are billions of phones out there. And each one is connected to the internet and has power and has a person taking care of it. And at night, they mostly just sit there.
Mm-hmm.
Imagine if you could take all those phones and connect them in a big network. They're spread out across the whole planet. And we thought, how many phones do we need in order to build a cosmic ray telescope the size of the Earth that can do science at the level of these like $100 million observatories? The answer is like only 5 or 10 million phones.
That's it?
That's it. You get enough of those, and we can see these super high energy cosmic rays at the same rate of these big observatories. But there's no limit. There's no like upper edge there. You have 50 million phones. You have 100 million phones. You have 1 billion phones.
Sure.
You could do cosmic physics the way nobody has ever done before. You could see these things at a higher rate. You could figure out where they're coming from in the sky. So that's the excitement of it. And so that's the project we're working on, is to figure out, like, does this actually work? If you have a bunch of phones, can you really reconstruct where this thing came from? So we have an app, and it runs on our phones. And recently we got a grant from the Julian Schwinger Foundation, which is a foundation that likes to fund proposals that have been rejected by the NSF. And I love it. It's like, hey, Let's invest in the crazy stuff.
Love
right?
it.
Right? Out of the box thinking. And we pitched this to the National Science Foundation like 10 years ago, and they were like, we love your idea, but first build it, prove that it works, then we'll consider funding it. Which on one hand is like, that sucks. On the other hand, like, I get it. You know, they either have to give their money to us and like our idea is not proven, or to like some existing experiment that they know is going to yield solid science. And that's the frustration, right? If you're at the NSF, you have to say no to lots of good ideas you'd love to fund. Why? Because they just don't get enough money. The NSF has intelligent people pitching them great ideas all the time, and they have to say no to most of them because there's just not enough money to go around. So they got to be conservative. I get it. But we pitched this to the Schringer Foundation. We said, give us enough money to build a small version of this so we can test it and prove it, and then maybe we can go global. So that's the idea. And it's a lot of fun. And, you know, potentially one day we'll have an app that can run on everybody's phone, well, you know, at night while they're not using it, or everybody's got an old phone they're not using.
Of
They
course.
could just plug it into the wall and turn it into a cosmic ray detector.
So if your app worked, is that something that we can beta right now, or?
It works, but the problem is that if everybody runs it, it's going to cost me a lot of money because you got to upload all that data to the cloud.
Oh, that's
And so
right.
We got to figure out a way to make it cheap and scalable and get real institutional support. So we don't have the funds to support a global network right now. Even if the phones exist already and they're already paid for, the infrastructure to gather that is expensive.
How much
So
data are we talking about that
Not a-
gets pushed?
Not a whole lot of data. Like we've really shrunk it so that it runs really slim on your phone, doesn't heat it up, doesn't need a lot of battery, doesn't upload a lot of data. Also, we don't want to be uploading photographs from inside people's bedrooms at night.
No.
So, you know, a lot of layers there of privacy, only upload individual pixels when we think there was a mu on there. So not a lot of data, but, you know, scale that to 10 million people, 100 million people. It's a lot of bytes. And, you know, cloud storage and cloud compute is expensive,
Yes.
especially these days when we're competing with, you know, AI companies. And so that's the hurdle is, can we prove that this thing works? And then can we figure out a way to scale it so that it doesn't blow the bank to do the cloud computation?
This idea is brilliant. Are there other applications for our cell phones that we're missing out on? Because it seems like it's a pretty complex device with
It is.
capabilities.
There's a lot of citizen science you can do with your phone. Absolutely. Phones can detect earthquakes because they have a little accelerometer.
Right?
You know, you can like, if you take hikes, you can see like the birds there. You can take pictures of them, contribute to all sorts of stuff. They're very powerful devices. And, you know, think about the scale of our investment in our phones versus how much we spend on science. It's dwarfed. It's absolutely dwarfed.
Right.
Like,
It's nothing.
how much money do we spend as a society on phones? It's big compared to science. And on one hand, that frustrates me. Like, why don't we spend more on science? On the other hand, it's an opportunity.
Yes.
Like, look, we have these things. We've invested in them. Let's figure out a way to use that investment to do some science. Because, you know, you got to operate in the real world.
Okay, so we get the funding, the apps work, the data comes to you. What does it mean? What do you do with that?
Yeah. So that's when you get to start asking questions.
Yeah.
Okay, so we see these showers are all coming from the center of the galaxy. Okay, what does that mean? I mean, is something at the center of the galaxy capable of creating these super high energy particles? What could it be? Now we can start training other kinds of telescopes there. Optical telescopes, infrared telescopes, ultraviolet telescopes. This is multi-messenger astronomy to understand the universe in several layers.
You can get trajectory information from
Absolutely.
that.
And you can get directions, right?
That sounds important.
Yes, absolutely. That's the goal. Is like figure out where in the world, where in the universe are these high energy particles coming from? We can make a map of the sky, of the galaxy, and say, where are they coming from? And we can't do that now because there's only like a handful of examples. So if we could get 10 times, 1,000 times as many, we could start to see the universe in this new way, right? And we know that the universe is emitting particles of this high energy using something that's new to us. And you know, I'm so jealous of astronomers and astrophysicists because, you know, we discover a new particle every 20 years. They discover something new and crazy like every year. There's something
Yeah.
like little red dots or this new thing or that weird thing. The universe is filled with surprises waiting for us to unravel. And so I hope we can build this cosmic ray telescope and we could identify where these things are coming from. Perhaps these things are like pollution from an alien particle accelerator. Somebody out there has built the Giga Collider, and this thing is just like occasionally spraying a particle our way.
That's the GoFundMe pitch right there.
That's the dream scenario. Or somebody else has a really fun theory. This is from a guy at the Institute for Advanced Science, like a real theory that these particles.
This is Einstein's old stomping grounds?
Yeah, exactly. Okay. Serious stuff is done there. He has a theory that these particles reveal a glitch in the simulation we live in.
Oh, I just got chills.
I know. So this fun theory, which is mostly just, fun to think about, that maybe we live in a simulation because the universe seems computational. The way we talk about physics is like, we know the situation in the universe now, we can predict it in the future, we can sort of step our way to determining the future. And that's sort of a computational way of thinking. And so it inspires people to think, oh, maybe our universe is a computer, ... right? Well, this guy's idea is, if the universe is a simulation, then, maybe they do it the way we would, which is like chop it up into blocks and simulate each of them in parallel.
Mm-hmm.
That works, except when things move really fast across the blocks, and so that you can't really separate them and do them in parallel. And so maybe the very fastest, highest energy cosmic rays, reveal the limitations of the simulation. It's just a fun idea. I'm not espousing this. I don't think the universe is a simulation.
You don't?
I don't. No, I don't think we really have evidence for that. I think if the universe,
if you break the Planck scale, then that's going to disappoint a lot of people, because that's the pixelation.
That's the pixelation of the universe. Yeah, exactly. We have no evidence that the universe is pixelated. Also, if the universe were a simulation, then the computer the simulation is running on is in some sort of meta universe, right? Not ours.
Right.
We know nothing about the laws of physics of that meta universe. And therefore, we know nothing about how that computer might operate. The computers in our universe operate a certain way because they take advantage of the laws of physics to do computation. You have bits, or you have qubits, or whatever your computer uses. It relies on the laws of physics. You have different laws of physics, totally different way to do computation. So if we know nothing about the laws of physics in that universe, then we know nothing about how computation works in that universe. So then we can't argue that computer works in a way similar to our computers.
But it doesn't have to. You're a programmer. Maybe the programmer said, in this experiment, this is Avogadro's number, speed of light, 186,000. This is their set of values. Let's see what happens there.
Yeah.
Couldn't that
Yeah, it certainly
work?
could be, but then you've lost the main argument. The main argument, as I see it, is our universe seems to work the same way our computers do. But if our universe is a simulation, it should work the way their computers do.
Why? Mario only runs to the right.
Mm-hmm.
Left and right on this, right?
No, you're right. It doesn't have to. It could be that their universe has different laws of physics, and they created a simulation for our laws of physics, which are different from theirs.
Yes.
Right? The way that, like, as you say, our video games don't reflect our laws of physics. But that's why Mario can't figure out he's in a simulation, because when he's looking at the way his simulation, if Mario built a computer, right, in Mario Land, he wouldn't be like, oh, like the computer I built is similar to the way my world works, therefore I'm in a simulation, right? He can't take that leap.
He can't, but a speedrunner playing it can find glitches in that program that were unintentional, that change the physics of the game.
Yeah.
So could there be glitches? If we're only at 5%,
theory, right? Yeah,
then
absolutely. Yeah.
I feel like anything's on it. I lean towards simulation.
You do?
I do. But
why is that?
Because of Planck, to be honest. Because everything just seems to be like we get to a certain spot and we can't see anything beyond it. And quantum mechanics, I hate that nobody knows, and the collapse of the wave function. Everyone's got a different idea, and we don't know. And I like things to just be neat and understood. So that's a way to reconcile in my mind. Like you're not meant to understand it. The programmer said you go here and no further.
Right.
But I don't know.
It could be. It could be.
It could be. You're arguing. I mean, if you get smaller, we got to start again.
Yeah. Yeah, and the simulation, the Planck scale is the limit of our current understanding, right?
Right.
And so it could be that we get down to that scale and the universe is very weird, or that it is really pixelated. You can't say one or the other. It's just the limit of our current understanding. It's
Right.
a cosmic sort of mental horizon.
And that's a great segue going into our next break is, you remember when, I don't know if it was the Tic Tac video UFO or whatever it was, the explanation was it's an object that violates our known physics, and that felt specific to me. So the question I want to talk about when we come back is, what happens if we meet aliens that don't think like us at all?
Yeah.
All
right.
Right back. What's your screenplay about? You write science fiction, no?
I do dabble in science fiction. I haven't written a screenplay, but
Okay.
of course I got a science fiction novel,
Sure.
or two in a drawer at home. I've got one about when scientists hear from aliens and what that message contains, and I don't want to spoil it. But, there's some interesting wrinkles there, and another one about how we might communicate with dark matter aliens.
Are these ready to go?
Oh yeah, I got novels. Absolutely, they're all done. Yeah.
Have you sent them out yet?
Oh, I'm working with an agent. Yeah, we'll see.
Perfect.
Yeah.
Excellent. Okay.
Yeah.
Because those two novels go right into what your book and what we're talking about
Okay.
is that if when aliens try to communicate with us or whatever, or sending signals out, we would never know.
Yeah.
How does that work?
It's a real challenge to imagine how we could decode an alien signal. I like to be optimistic, and I love SETI, and I'm glad that people are listening to the sky, because if somebody's shouting at us and we're not paying attention, God, what a tragedy, right?
Right.
But it's also, if you think about it from the point of view of like language and translation and encodings, hard to imagine a scenario where aliens send us a message and we figure out how to transform that message, which they've had to encode using some kind of symbolic logic to transmit it to us, how to reverse that encoding so it comes into like ideas in our minds, right? Think about like the messages that we've sent to space. We sent the Pioneer plaque, right?
Sure.
Which is this like doodle by Frank Drake and Carl Sagan,
Yep.
and it's got like the pulsar map to how to get to Earth, and it's got a little diagram of like, a spin flip transition. It's got lots of cool
Sure.
physics encoded in it.
Hydrogen's in there, I think.
Hydrogen
Yeah.
is in there for sure.
And that wasn't a good move?
Well, it's well intentioned.
Okay.
And I don't know that I could have done any better, but it's basically an impossible task. They did the obvious thing. They said, well, we're not going to use English. We're not even going to use like math symbols. It'd be foolish to imagine that like aliens think of plus and equals and minus, right?
Right.
So they tried to use pictures and little diagrams. The motivation was, let's come up with a universal language, a language which decodes itself, which you can just look at and you don't have to guess. But there's so much of human culture in how they wrote down those ideas, how they encoded those ideas, that you'd have to basically be a human to look at that and know what they're talking about. And, philosophers of language who I spoke to in researching my book, they're very pessimistic of the idea that we could get a message.
Hang on. Don't just blast over that. You cold emailed Noam Chomsky and wrote back to,
That's
right?
true, yeah.
Right?
Yeah, so I was wondering, like, look, how could we communicate with aliens? Is it possible?
This is what you asked him?
Yeah, because I thought, look, who has thought about, the boundaries of language and is a little wacky and is famous for answering emails. And so I did cold email Noam Chomsky and asked him, like, look, how would you communicate with aliens? And he wrote back and he said, I actually had a whole conversation with him. He agreed to a long phone call. And he said arithmetic. He said probably math and, start with 1 + 1 = 2 and build up logic from there.
Or Isaac Asimov, prime numbers, that sort of thing.
Yeah. And, it'd be much easier if aliens were here, because then we could do things like we could say, this is 1, this is 1, this is 2. We could build up those kind of things. But even to get to 1 + 1 = 2 with a distant alien civilization where all we have are messages, that's really hard to imagine ever working. And the reason is that translation of ideas to symbols. We don't think about it very much, but when we talk, when we communicate, we're always taking an idea and transforming it, encoding it somehow, right? I write you an email, I'm using letters. I talk to you, I'm pushing sound. There's nothing inherent about the message I'm sending that lets you know how I encoded it, unless we agree. Like you and I both speak English, so we can use English to communicate. Somebody else uses math, we can use math to communicate. But if you don't know the language I'm speaking, how could you figure it out? It's tempting to say, like, oh, we could crack the code. But if you don't know how it's encoded, and you also don't know when you've decoded it, then how are you ever going to crack it? You get an alien message, you try this decoding. I don't know. Is this what they were saying? You try that decoding. I don't know. Is this what they were saying? It's not like in World War II, where when you guess the Enigma machine, all of a sudden you get plain text that makes sense.
Right.
This is an alien message. Who knows when it makes sense? And so if we just get a message from space, we may never know how to decode it. We may never even recognize that it is a message. Take, for example, the wow signal, right?
Mm-hmm.
This huge pulse of energy in exactly the way astronomers say we should be contacted.
Sure.
But what's the information content? It was like very brief, this little blip. Is there information content? Was it just some hydrogen burp somewhere? Or was it aliens? And they sent us what seems to be an obvious message, but we don't know how to decode it, how to even begin, right? Like, what's in there? And that's the reason why people don't think the wow message is from aliens, or people can't conclude that, because to make that leap, you not only got to get the message, you got to be able to decode it and say, like, oh, they're from this place and they're talking to us about that. So while I'm a big fan of SETI and I hope that they hear something understandable, I think that it's much more likely if aliens are communicating with us, we either can't recognize it or could never decode it. And, people out there who are skeptical might think, wait a second, but we can decode things like we've decoded Egyptian hieroglyphics, right? Yes, we did decode Egyptian hieroglyphics, but that was easy. We had a cheat. We had the Rosetta Stone.
Yes.
Right?
And it still took 20, 30 years?
20 or 30 years, right? Imagine, why did it take so long? It's because we had a bunch of cultural assumptions about how hieroglyphics worked that were wrong, that led us down the wrong path. Even when we had the Rosetta Stone, even with the cheat sheet, right?
Yes.
So our cultural assumptions, the things we imagine must be true about communication, blind us to be able to decode even messages from other human beings, right? Ancient human cultures. And so the idea that we could do that for aliens, I'm not going to say it's impossible. I'm saying it's maybe wishful thinking.
Didn't you run that Pioneer plaque by your students as an experiment?
Yeah.
And they crushed it, right?
No.
No.
They didn't. If you show this diagram from the Pioneer plaque to people who've never seen it before,
Yeah.
and my students are young enough to have never looked at this before, and I asked them, I said, what do you think this means? I was wondering, like, is this, well enough defined, well enough designed that a human will understand what Carl Sagan meant? And these are human brains. These are physics-trained brains. They're like the closest thing you can imagine to the person who wrote the message, and so it should work well. This is the best-case scenario. And they sat there for hours guessing this, guessing that, guessing the other thing. Nobody came anywhere close to the right answer, right? And again, I don't want to dump on Carl Sagan. The man's a genius, a pioneer in many ways. I don't know that I could have done better. It's an impossible task to write a self-decoding message that works for a universal audience, no matter what their culture, what their context. It just can't be done. Professors of philosophy of language say that's impossible. So that doesn't mean the whole thing, there's no hope, right? If aliens arrive and we can talk to them, we can point at stuff, we can develop a language in common, then we can make progress. But distant communication between the stars, I don't know if that's ever going to work.
Your experiment reminded me of something. If you would indulge me a quick story, you're a sci-fi fan, and this is for people listening to maybe help them. There's this great Star Trek Next Generation episode called Darmok.
Okay.
And the Enterprise arrives at the planet. They're trying to communicate with these aliens. The universal translators work. So the words are getting through.
All right.
But the aliens are speaking. They're saying Darmok and Jalad at Tanagra. Temba, his arms wide. Shaga, when the walls fell. So we're understanding the words, but the thing was, these aliens were speaking in metaphor of their mythology. So it would be like us talking to an alien speaking perfect English, and I say, well, my Achilles heel is this. Or,
Right.
if I do that, I'm crossing the Rubicon.
Exactly.
So even if you have the language, without the cultural foundation,
Exactly.
we're stuck.
Yeah.
So I'm kind of with you. I think it's a big challenge.
And I think that we are not good at imagining how big a challenge it could be. Because, look at Star Trek: The Next Generation. It's great, and I love it. But, the aliens, they're like humans with a croissant on their forehead.
Yes.
And you're surely things are going to be more different than that. And, it's not just their physiology, but their minds are going to be more alien than we can anticipate. And I think we should think creatively about what aliens might be like, but we should also accept that we're probably incapable of really anticipating it. That more likely they're going to be much more alien than we can imagine. And that's going to be a wonderful moment, because then we're going to be like, what? That's even possible? How does that work? The scenario you describe, you get to learn about a whole mythology of alien culture. How fun, right? So, these are good problems to have. If we meet the aliens and there's a barrier there, it means that, we got to start small. We got to figure out how to get there. There's a lot to learn still. And we should pay attention along the way to what it says about our humanity, what it says about their alienness, that we're having this obstacle.
Well, what about the theory that life is going to evolve sort of the same way-ish everywhere? Bipedalism, where symmetry, the brain is up top. No?
Perhaps, right?
Perhaps is pretty close to no, actually.
Well, for that to happen, you'd have to have the same evolutionary environment,
Right.
and the same accidents, the same mutations.
Right.
It's possible, but if an asteroid hadn't hit the Earth 65 million years ago, we wouldn't be here, right? So
True.
why should we expect the same exact scenario to happen elsewhere? Seems pretty unlikely to me. And it's extrapolating from an example of one, right?
Right.
Which is all we can do. This is all we have. And so we're very, very limited. But if I had to place a bet, I would guess that aliens are going to look very different, and they're going to act very different and think very different. But, there are clever people who think that there are some things that they'll have in common, There's a great book called The Zoologist's Guide to the Galaxy, where he thinks about what animals might be like on alien planets. And, he says, look, anywhere there are critters, there's going to be critters eating other critters. So, for example, predation will exist everywhere. And that's probably true. That makes sense, But he could be wrong, right? A lot of this is cases where we don't know where we're making assumptions. And the joy of experimental work, of going out to explore the universe and not just thinking about it, is being wrong, is discovering where your assumptions have blinded you.
Right. Aliens saying, why did they use carbon when silicon-based life is, or arsenic? Why did they, right?
Yeah.
Why did they go that way?
Yeah, exactly.
So you don't believe aliens are here? I'm not putting you on the spot or trying to be weird. I'm just, because we talk about when they're going to be here, when they're going to be here. So you don't think they're here?
I don't know that they're here. I certainly haven't seen evidence that compels me to believe that they're here. I want them to be here.
You do?
Oh, yes.
You're not a dark forest guy.
No, I want them to show up. Look, even if the aliens show up and they kill most of us, they eat half of us, as long as they deliver some answers about these physics questions, it's a fair deal from my perspective.
I'm not sure if the wife and kids would agree.
No, they probably don't. But I'm just so desperate to know. I mean, imagine there are answers to these questions out there. People, things, aliens know them. They could share them with us. Aliens are flying by. Are you not going to flag them down? I mean, really?
Yeah.
You want to remain ignorant? I mean, I get the risk, the existential risk to humanity of attracting attention of super advanced aliens. I get it. But I could not stay quiet. You give me that big red button, I am mashing it because I just got to know. And, the idea that the answers exist and we're just not going to get access, that's infuriating to me. That's so frustrating. So yeah, I definitely want to know the answers, even if there's a great risk to Earth. Are they here now? There's a lot of talk about that, and there's a lot of videos, and a lot of people want them to be here, and I want them to be here. I wish that they were. I want those videos to be true, but there's too many prosaic explanations for basically everything.
Yes.
And too many things that don't really add up for me to believe that they're here. And I'm a science guy. I got to see an overwhelming evidence, physical evidence, independent replication before you believe that kind of stuff. But I'm not biased against it. If anything, I'm skeptical about it because I'm biased towards it. And you got to be extra skeptical of things you want to believe, because that's the easiest way to fool yourself.
That's very well said, and that's very true. And I lean toward disclosure is probably not going to happen, or at least not going to happen the way people hope it's going to happen.
I'm certainly a fan of disclosure. Like, it should all be out there.
Sure.
Like, if there are secrets, bring them out, Epstein files, alien files, whatever, air it all out. I think there's a lot of harm done by secrecy, a lot of lack of trust, which is well deserved, because there's been a lot of secrets, which I think are unfortunate.
So the ship lands in your backyard, Klaatu comes out, you get one question. You get one. You just get one. No follow. You just get one. Phone a friend. What's the big one?
Well, I think I answered that question with my feet. I devoted my whole life to answering one question, which is, what is the universe made out of? That's the one I really want to know the answer to. And if I get one question for the aliens, that's going to be my question.
Made out of, do you mean the fundamental, down to the...
Yeah. At the firmament.
The firmament.
What are the ingredients of the universe that are unavoidable, right? That always exist? Because there's lots of things in the universe which exist, but they don't have to. Kittens, for example.
Mm-hmm.
A lot of time when the universe didn't have any kittens in it.
That was a very sad time.
I know. Yeah, the pre-kitten era was a bad time. And, it doesn't have to have kittens. What does a universe always have to be a universe? We don't even know if that includes space and time. It could be that space itself is emergent, right? That it's something so deep down that we don't understand even how to think about it. And that's what I want to know, because that gives you the best access to those philosophical answers. This is what the universe has to always have to be a universe. Then that defines what it is to be a universe. And it might give you some insight into why we have a universe. Why is there something and not nothing? Why is it this way and not some other way? When I think about getting that answer, I wonder if it'll be self-evident. If you look at it and you think, oh, of course, this is the only way it possibly could be. Or if you look at it and you're like, there's a 7 in it. Why is there a 7? Is the universe 7-ish? Why couldn't it be 6-ish? I wonder about the nature of those answers and what it would mean. But yeah, that would definitely be my question.
It's a great question because we know for a fact there is something, just because of dark matter. So there is something more.
Yeah, there's definitely more to learn. What we don't know is if there is a foundational anything.
Right.
It could be that because we've never seen anything that's foundational. Everything we've ever seen is made of something else. So even the idea that there could be something which is only made of itself and not made of something smaller.
So a quark has a smaller component?
Well, we don't know, right? But it seems likely because
it does.
There's a pattern to the quarks. There are unexplained patterns among the quarks and the leptons that look a lot like the patterns in the periodic table.
Wait, explain that, because I haven't heard that. There are patterns to the quarks that look like the periodic table?
Yeah. So back up 100 years, you have the periodic table. These are the things that define the universe, 100 elements. But there are patterns to them, right?
Sure.
Some are conducting, some are not conducting, et cetera, et cetera. It's a periodic table for a reason, right? And we now know that those periodic attributes of the periodic table are emergent phenomenon from microscopic structure. Mm-hmm. How the electron orbitals come together, et cetera. Everything comes out of that. So now, fast forward, we're looking at the table of the quarks and the leptons, right? We have 6 quarks, we have 6 leptons, and this is the new periodic table. And there are patterns there that we do not understand. Like, why are there 3 families of quarks? Why are there 3 families of leptons? Why do those match perfectly? why is the electron charge exactly balance the proton, which is 3 quarks mixed together? Not like 2 within 1% or 0.01%, exactly matches. Right? Our theory doesn't explain that. Those are 2 parameters in our theory. Why do they have to be set this way? Why do they get more massive as you go up in the generations? Nobody knows. It's a whole set of questions you can ask about this, which probably are explained by some microscopic structure. It's emergent properties of something smaller that we don't yet understand.
Of course, because there's clear intention there, whether it's God or something else, but there's intentionality to that.
Well, I'm not sure about intentionality, but there's definitely structure there.
I just mean structure, yes.
Yeah, okay,
like it's organized.
Yes, exactly. And so we've seen this before, and it's always been explained by new microscopic structure. And so it could be that that's the last one, that once we understand that the quarks and the leptons are made of the same little squiggly-ons or whatever,
right.
That's it. But probably there's going to be structure to those and patterns there we don't understand. And then we'll go deeper. And it could be we just do that forever, right? It could be that there's no base case. It's like recursion, but it just keeps going.
Right.
Right? Because we've never seen anything that's not made of smaller stuff. So how do we even know that anything like that exists? The usual argument is Planck scale, but that's a misunderstanding, right? That's just the limit of our current theories. We don't know that it can't go on beyond that. So it could just be that it goes on forever. And philosophers are cool with this. They're like, yeah, it could certainly be that everything is built out of something, which is built out of something else, which is built out of something else, and it recurs down forever. It's a crazy way to imagine the universe working, but we have no argument against that.
No.
So
there's a logic to that bothers me.
Right? Yeah, exactly.
When you finally get smaller than quarks, it's like, oh, but wait, there's more.
Exactly. Quarkitos.
How much of a setback was it when Congress pulled the funding for that Texas Collider back in the 90s?
Oh, it's painful. It's painful.
It was going to be bigger than Hadron, no?
Yeah, absolutely. It was going to be much bigger than the Large Hadron Collider is now. So it just set us back decades in our understanding of the universe. And if they had finished that thing and turned it on, we would have discovered the Higgs boson in the 90s.
Right.
And we could have potentially discovered stuff which the LHC still can't see, right? Who knows? It's over our current horizon. I don't know if it would have been over that horizon. But yeah, it set us back. And, it's a tiny amount of money on the scale of countries. It's a few $1 billion.
It's so small. It's so small.
It's frustrating. Yeah, we could have just bought that knowledge. We are kids in a candy store. It's all around us. We got the money in our pockets, and we're just like, nah. I don't want to buy the secret to the universe.
Gravitons aren't that cool.
Yeah, I want to spend on something else. And, I shouldn't dictate public policy, and no science should, but I think it's important that people understand the science when they're making these decisions, so they understand the context and the consequence of these decisions.
That's why I asked about gatekeeping, because you need the public support. That's why I love wacky experiments. You have to inspire the public to support science.
Science is by the people, for the people, and of the people, right?
That's right.
And there's no division. It's not like scientists are a different breed. Like, we're just people. Right? We're just people who are curious about the universe and decided to devote our lives to it and get this privilege to do this with our lives and our minds. But we're just people just like everybody else. We're curious about the universe, and science should be shared with everybody. Absolutely.
Yeah, and I think scientists and artists are the 2 most important types of people that we create. So when there's when Avi Loeb rents a boat and drags a magnet across the South Pacific looking for pieces of a meteor, sounds like a crazy thing, but that is science that makes people excited. Because it's what? He couldn't get it funded. He got it a little bit of funding, but we should be throwing money at that kind of stuff. Oh, it drives me crazy. But there's no solution, not that I can think of.
Well, let's just 10x our funding for science. That would solve a lot of these problems, because then we'd have enough money to do like your mainstream science and your crazy ideas. And a lot of the institutional pressures which lead to the issues we have today would be released if we had just more money for science.
Sure, where do we sign? Because isn't the Manhattan Project kind of annoying? Because we proved we can do it.
Yeah.
We can do it.
Yeah.
We just doing it for the wrong reasons.
Yeah, but to do that, we need to convince people,
Mhm.
right? Because it's the people who decide. We need to convince people that science is worth the investment and that we're being responsible with their money because it's their money. And I think we have a long way to go there. And science is under attack right now, unfortunately. And I think,
What do you mean?
well, I think there's there's a lot of anti-expertise sentiment out there, and I think there's a lot of folks who are encouraging that and trying to undermine the role of science in public discourse.
Can you be more specific? But if you're talking about specific names, you don't have to do that. But I haven't heard science under attack. That's
Well, the funding for science, for example, is certainly shrinking.
Of course.
Right? And I think that's because we see a lessening of support for science among the public. And I see a sentiment when I interact with people online that a lot of folks out there seem to be under the impression that scientists are committing fraud or just like slurping up money in bad faith, proposing theories that they know don't make sense just to try to capture government dollars or whatever. Things that don't resemble the reality I see on the ground. Like I talk to scientists, nobody's out there like trying to cook up theories that they don't believe. They're working their best to try to understand the universe, and everybody disagrees. Some people think that research is a waste of time and money. I think that my research is the best way we should do it, and everybody disagrees about the way forward. It's important we remember that it's important that we assume at least that everybody's operating in good faith, and that we focus on the arguments rather than trying to attack people's motives. Like, where's the evidence? And what's the argument for this? And let's keep it based in the science.
I've heard the Higgs being the last discovery in 2012 described as the nightmare scenario. Because I hear that it's like there's nothing more. It's been years, so why bother? I don't know what the good response to that is. What can we show people and show them that it is moving forward? It's not. We haven't stagnated, have we?
So it's a good point, and the thing to remember is that research is exploration, and we shouldn't be making promises about what we're going to discover because we just don't know. And there's going to be dry spells, and then there's going to be periods where we discover lots and lots of stuff, and nobody knows what's over the cosmic horizon. And so we shouldn't be promising discoveries. And I think certainly some people, went out with public statements that were too strong. I don't think majority of scientists felt that way. So it's fair to say, like, we hope we would have discovered more. I hoped so also. I also wish that when they landed on Mars, they had discovered, little critters crawling around. But nobody says that, like, NASA has stagnated in their exploration of Mars. It's a wonderful program. Their machines are working very, very well, and I encourage them more. And we should do more of that exploration.
Sure, but what's their budget percentage-wise compared to 1969?
Yeah, exactly.
It's like nothing.
It's nothing. It's unfortunate.
Because once again, there's no military reason to do it. That's just what it always comes down to, unfortunately.
Yeah, and so has physics stagnated? More broadly, there's been a lot of really interesting developments in physics outside of experimental particle physics,
Yeah, now they're driving antimatter around campuses.
Absolutely.
Which sounds like a great idea.
Absolutely. But, we can't control where the discoveries are. We can just do our best to explore, build these machines, if the public will pay for them, and hope that we can make these discoveries. And so, yeah, it's a little bit of a nightmare, but it's also our reality.
We need the discoveries. Oh, speaking of antimatter, this reminds me, and getting the public support. You've heard of the Albuquerque drive, the warp drive?
Sure.
Can that really work? Can we fold space-time like that? And we don't have to do ooh. This is science.
Yeah. Real science.
Yeah.
I love this idea, and I love that it shows how science works. You don't go all the way to the solution immediately. You start, you play around, you suggest an idea which has obvious problems, and then you attack those problems, you work on it. It's serious science, and it can be the first step towards a warp drive. It has big current problems. One of those is that we don't know how to build the thing.
Right.
General relativity says it's allowed to exist, like space can have that configuration. That's not the same as we know how to make space go from our current configuration to that configuration. It's like if somebody says, hey, a souffle is possible. Okay, that doesn't mean I know how to make a souffle, put me in the kitchen, I'm mostly going to not make souffles,
Yeah, I fail most
Right.
of the time with those.
right? And so we don't know how to go from not a warp drive to a warp drive. And there's no guarantee that every step along the way satisfies the equations. The warp drive itself satisfies the equations. Our current situation satisfies it, but every step along the way has to also not violate the laws of physics.
Right.
So that's a big question mark. Another question mark is like, even if you could build the thing, would it do what you wanted? Because the current explanation, because the current design requires you to arrange matter basically in a track between where you are and where you want to go.
Mm-hmm.
And like, all right, cool. If you built the track, then you could get there, but then you're already there. So if the goal is to like get to Alpha Centauri in a short amount of time, first you have to build a track in slow sublight travel between here and Alpha Centauri. Then you can get to Alpha Centauri.
I hadn't considered that. So in order to fold the space, you already need to track the space.
Yes, exactly. So it's, you know, it's great. Somebody builds the train track. You can get across the country much faster, but the first person still has to build the track. And so we'll already be there. It's not a way you can explore the universe. It's a way you can more rapidly get from places you've been to places you've already been.
Can we? Well, I hadn't considered that, so we have to throw that out now. Can we build the craft to navigate the bulk, the RS1 bulk? Can we vibrate to a higher dimension where space compacts exponentially and navigate?
Yeah, we don't know. We're not even close to knowing the answer to that because we don't know if space operates that way. Is there a bulk? Is there 5 dimensions? What are the laws in those dimensions?
What does your gut tell you though? You're a science fiction writer, so you can't tell me you haven't thought about it. This is fun. This is the fun part.
Yeah, sure. I suspect that there are ways to get from here to other stars faster than light would go. My gut tells me that there's a way. You know, that there are loopholes. I don't know that it's warp drives. I don't know that it's wormholes. But I suspect that we'll come up with a clever way to escape our, you know, the cosmic imprisonment of the speed of light and explore the galaxy. I don't know exactly what that is yet.
You don't?
No.
I wish you didn't say, because I had a follow-up. But so in your novels, I guess the aliens come to us, huh?
Yeah.
How did they get here?
Well, if they're dark matter aliens, they could already be here.
And they're already here.
Right? That's
true.
the amazing thing about the dark matter universe. It's like another universe layered on top of ours, right?
Mhm.
Dark matter's in the room with us right now. It's here, right? And so aliens could be aliens, but also neighbors.
Right. What do they look like in your book? How do they?
I'm going to save that detail.
Save it. Oh, okay. I guess because you're publishing it, it's fair to wait.
Well, I hope to. We'll see.
But you think that we'll get there someday?
You know, I'm an optimist. I like to believe in human ingenuity.
Yep.
In human creativity. And anytime somebody has said, this is impossible, somebody's figured out a way to do it, you know, and we know we have hints already, like these warp drives and wormholes. These are hints that the limits we think about are flexible, right? You know, the limit to the speed of light is the limit for things moving in flat space. But the universe is expanding. It's not flat. And the universe can be curved. So there's you know, strong hints there that there's something we can do to escape those cosmic limits. A warp drive's not workable yet. Wormholes we don't know how to build yet either. But probably somebody else is going to come up with something even more clever.
Yeah, and what's cool about those is mathematically, at least, it works, or it's close enough. Like we're still speed of light. We're not touching it. You know.
Yeah.
I do like the theory of a circular craft that's a particle accelerator creating a field and moving into the bulk. I love that because, I mean, RS1 says you could do that. Now, I believe the theory is that it's at the quantum level. You can't really scale that, but it's there.
Yeah.
It's published, and I think the math works, except the experiments failed. So I just like that stuff is out there, and it's so cool that physicists are building a UFO separately and then don't even know it. I love it. Your contributions to the UFO, I really appreciate them. I'm looking at my notes about your Starbucks moment story, where you talked about, and it was about communicating with aliens. You talked about traveling.
I think fundamentally, I'm hoping that when the aliens arrive, that they teach us something new and unexpected about the universe. And that hope for me comes from, everyday experience. The reason that you travel the globe to try to experience new things is because you can't imagine everything that humans can do and the way humans can live. Like, if you go around the world, you discover people have weird stuff for breakfast, right? They don't just all have your same Starbucks order. They don't even have Starbucks everywhere. And how disappointing and boring would it be if you went to some new part of the world and all they did was everything you already do, right? The reason you go is to have that moment where you're like, what? People have like spicy fish soup for breakfast? I never imagined it. And then it becomes your new favorite thing.
Sure.
Right? And you're like, and that tells you that you're not capable of imagining every way it is to be human, every way to experience and enjoy the world. And so when aliens come, it's very likely that they're going to show us new ways of being in the universe, not just what we have for breakfast, spicy alien soup, but new ways of doing physics and new ways of doing science. And that's going to tell us not just about what it's like to be an alien, but also what it means to be human. It tells you something about yourself, that you are capable of imagining these things or you like these things. And so I hope when the aliens show up that they deliver some insights into the nature of humanity, as well as insights into the nature of physics and the universe. I think we're going to learn a lot about both when the aliens show up, if they don't just zap us from space.
I tend to think they wouldn't do that. There's plenty of resources out there, and hopefully we're not tasty.
Now, and following up on that,
yeah,
I agree with you. And I think that in most science fiction stories, like, why are we fighting over resources? There's like asteroids full of platinum and planets made of water.
Right.
The thing that's maybe unusual about Earth is us,
mm-hmm.
right? Intelligence, technology. So I think if they come, they might, enslave us to work in their science factories or whatever. But I think they're less likely to kill us.
Right.
Why travel all this way just to do that?
I think they probably enslaved us to mine gold to save their atmosphere, but I have no proof. That brings up something I wanted to ask you about is you have an extension to the Drake equation, yeah? How does that work? So Drake equation, if you could just tell us what that is and then how you messed it up.
Yeah, so the Drake equation is a fun way to think about answering a really hard problem. And that problem is trying to calculate how many alien civilizations are there out there that could communicate with us. And this is something Frank Drake was worried about. And the answer is really elegant, but it's also really profound. He says, look, just break it up into pieces and start with how many stars are there? And then what fraction of those stars have planets? And what fraction of those planets have intelligent life? And what fraction of those have civilizations, et cetera, et cetera. And, it's the Drake equation. It's just a bunch of numbers multiplied by each other, right? And that sounds really simple and kind of trivial. And like you look at other famous equations like, the Schrodinger equation, like complex numbers and all sorts of crazy stuff in it. Why is the Drake equation famous? It's famous because the structure of it is really insightful. The fact that you have to multiply these numbers together tells you if any of those numbers are zero, the answer is zero, right?
Yeah.
It doesn't matter how many stars there are if none of them have planets, or if none of those planets have life, or if none of those have intelligent life. If any of those numbers are zero, the answer is zero. Right. And that's a little depressing.
It is.
It tells you everything has to go right in order for this to work. So when we were thinking for our book about the deeper question, like, well, not only are we interested in aliens, we're interested in, are there aliens out there we can talk about physics with? When they show up, we can like go to the blackboard and start writing Lagrangians and thinking about the nature of space-time. And to do that, we have to make even more requirements. We have to have aliens that exist and do and are technological, but also, do they even do science? Can we communicate with them? Do they ask the same questions? Would they accept the same kind of answers? So all these things need to be in place for this like fantasy scenario where aliens show up and then we're like talking about physics 10 minutes later. For that to come to pass, all those things need to happen. And
none of them can be zero once again, right?
That's right. None of them can be zero. If aliens don't do science, then there's no way we're talking to them about physics. Or if we can't communicate with them, then like it's all over. And in the book, we go through each of these in turn and ask, well, like, what are the chances? What do we really know? And we argue both sides of it, of course. And Unfortunately, we don't have an answer. The same way we don't know the answer to the Drake equation. The thing that's cool about the Drake equation is that you can see us making progress. Like when
Yes.
Drake put it together, he knew very little about any of those numbers, maybe the number of stars in the universe or in the galaxy. Now we know, like, that most of those stars have planets.
Right,
It's
so
a huge leap
It
forward.
was huge, so no
right?
zero there.
Yeah.
Now we keep going.
Like, and I don't think enough people are excited about that. Like, we had this turning point in human history, 1995,
Mhm.
when we went from we've seen less than 10 planets in the universe to like now we've seen more. Now we know that there are planets elsewhere. Before that, it could have just been that our solar system was the only one with planets.
That's right.
Right? For all we know, this is the only example. Maybe we live here because it's weird.
And I think we're over 5,000 exoplanets now.
That's right. And
Imaging some.
I know. And we can extrapolate from that the likelihood of any star to have a planet. And it's a shockingly high number.
Yes.
Right? It's, 50-ish% have like Earth-like planets in the Goldilocks region. It's an incredible number. A huge number of stars out there with planets. But we don't know if the next number is zero.
Right.
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 But we're making progress, right? We're like imaging those planets. We're looking at their atmospheres. We're finding potential biomarkers of life. And it could be that pretty soon we discover, wow, there's life everywhere. Maybe most of it's microbial, so we got to work on the next number.
Mhm.
But
But that still counts to me.
it still counts.
Yeah.
And so I'm excited about like how humanity makes progress on these questions. And I hope that one day we get to start answering some of the questions in our extended Drake equation. Like, well, do aliens do science? Like, could they show up with their warp drives, but they're not scientific? They're like not interested in understanding how they work?
How could that be? How could you have interstellar travel without understanding how to do it?
Well, the same way that we had technology for centuries, thousands of years without understanding how we did it. The same way I make a souffle in the kitchen without knowing what's going on inside because I don't know the food chemistry. We had metallurgy, we had fermentation, we had all sorts of technology that we didn't understand. The guys who knew how to make like super sharp samurai swords, they didn't understand, the solid state physics of what was going on there, the doping and the steel and the structure of that. They just knew how to do it.
I guess that's true.
You dip it this way, you turn it that
Right.
way, you hammer it this other way, right? And before we had what we call modern science, we were sort of stumbling around in the dark, developing technology slowly. Science absolutely has sped that up because knowing how things work means you can modify it, you can extrapolate, you can predict, but it's not necessary. You can develop technology without understanding how things work. And it's maybe less likely, but it's certainly worth considering the possibility that aliens could, like, over millions of years, stumble their way into this technology. And they show up and they can show us how to build a warp drive. You do this, you bang it that way, you dip it in water, you put chocolate on
Right.
it, whatever.
Right.
And then we're like, okay, but what is that? How is it working? What's the quantum gravity of it? And they're like, we don't know. And why do
Right.
you care?
Who cares? It works.
Right? And you might think that's impossible, but that curiosity we were talking about early on, where we want to know, I want to know how it works, but somebody else is curious about something else, right? The way, like, I don't really care about food chemistry. Somebody out there is devoting their life to it. There's like labs of people working on food chemistry. They couldn't imagine not wanting to know. Curiosity is an emotional response to the universe.
Sure.
And it differs from person to person. It must certainly differ from human to alien.
It has
right?
to.
Right? So to imagine that aliens have to have the same curiosity about the universe that we have, that's projection. That's saying they're just like humans with a croissant on their forehead once again. Right?
That's right.
And they could be very alien. So I think, you can make an argument that aliens that are curious the way we are more likely to develop science and therefore technology. So out of 100 visiting aliens, probably 99 of them know how their warp drive work. But it's not a requirement, right? And so it's just an argument to say, look, avoid making human-based assumptions here because we don't know.
So I think sooner or later we'll see that most of Drake's filters are going to be greater than zero. What do you think of your extension? What's the hardest one to overcome? What's the most difficult filter? The one that, man, I don't know if we're going to get there.
I think one of the most challenging one is, the answers. I think even if aliens are curious and we can communicate with them and they want answers to the same questions, it could just be that their answers don't grok with ours, that they give us their answers and we're just, I don't get it, or it doesn't work for me, because in the end, there's not an objective way to evaluate whether an answer makes sense to you. It either makes sense to you or it doesn't, and you demand more explanations or you're done. That moment when you stop, it's not an objective moment. It's a subjective decision. So I think I get it enough to move on. And so it could just be that aliens have answers that don't satisfy us, right? And they don't know why. They're like, what do you mean? We explained it to you. Here it is. And you're like, it's not working. Because of those reasons we talked about earlier, that we have this intuitive library of concepts in our mind and we demand everything mapped to those. And if they don't, then we're like, well, it's not really working. So to me, that's sort of the nightmare scenario. That's the hardest one to imagine, knowing how to cross that barrier. There's other scenarios that are easier. Like, what if aliens show up and they have a theory of the universe, but it's just very different from ours? Like, their whole history has been different. They have a whole development of math and physics and whatever, taken a totally different path, and they've arrived at a different theory. We have quantum fields, they have quantum schmields,
right?
Whatever, and they're very different. That's frustrating, but it's also it's bridgeable. We can be like, well,
Sure.
Your theory works too. That's cool. Maybe there's some things that are easier in your theory and some things that are easier in ours, right? And it means something deep about the universe if there are two explanations.
That says a lot about the universe.
Right? It means that ours is almost certainly not reality.
Correct.
Right? If there's two explanations. But you could live with that, right?
Sure.
You could live with that. But the idea that aliens could show up and their explanations just don't sit with us, I don't know how to overcome that. So that's the one that keeps me up at night.
Does it really keep you, when you say keeps you up at night, do you really, are you emotional about this? Honestly, I mean, with what physicists, like astronomers, say, I've spoken to several astronomers that are frightened. And frightened in a way, meaning like the more I know, the smaller I feel and insignificant, but they're still driven by the curiosity. And you're looking at particles. How does that make you feel as a person? More insignificant, more significant? Is the universe a scary place? Is all this an accident? These are questions that I would have asked because you're looking at the fundamental building blocks.
Yeah. I find the universe very welcoming. I mean, so far, this technique we developed, I find the universe very welcoming. I mean, so far, this technique we've developed, it's unraveling the secrets of the universe. They're unfolding before our eyes. No problem has been too hard so far. It's incredible to me that it's worked as well as it has, that our minds are capable of this. So to me, it's joyous. It's exciting. It's incredible what we've learned. And I just want to be around long enough to be along for the ride when we uncover the next crazy discovery. So I don't know why that is, why it works so well, why we're capable of understanding it, why the universe even follows laws that are discoverable by experiment. It's amazing. So I'm thrilled to be a part of this universe. It's the tiniest, smallest little mote of dust in a tiny corner of it that can yet unravel the way that it works. I mean, think about this. We've never left the neighborhood where we grew up, right? Maybe we sent somebody to the moon a few times, right? We've sent satellites and robots to Mars. We've gone nowhere. And yet, by staying at home, we've still made a map of almost the whole universe, right? Of how things work from the cosmic to the microscopic. It's incredible just by receiving the photons that land here on Earth. So imagine what we could do if we actually began to explore. Go visit these things and sample from them and orbit black holes and stuff. The kind of things we learn, I can't even imagine. So I'm excited about it.
So day in, day out, the excitement sustains?
Absolutely. It's a joy to wake up and go to work and think about these things, and especially actually the science communication. Like, I love connecting with the public about it because it reminds me of why we're doing this, and it shows me how many people out there are excited about this. People who always had an interest in physics but ended up doing something else for whatever reason. They don't lose that curiosity. They still want to know and they want to participate. And, that's why I love shows like yours and our show that try to share it with everybody. Make sure that, because it belongs to everybody, that everybody gets to participate in this joy and this miracle of understanding.
What's the last non-physics scientific discovery that got you excited, that made you run home? What was the last thing?
Non-physics.
Non-physics. If it's physics, it's okay.
I think something that's super fascinating is how we understand our own history, how we came to be who we are.
In what way? How far back are we talking?
I'm talking about the development of humanity, million years.
Okay.
And, Homo sapiens, and how we know about like Homo sapiens interbreeding with Neanderthals.
Oh, yeah.
And we can tell like whether it was a male or a female because does it come in mitochondrial DNA or on the Y chromosome? It's amazing to me how we've unraveled this ancient history through the tiniest of clues, right? And what we've been able to piece together, it's like amazing detective work for millions-year-old mystery. And I can't wait to learn, what they're going to continue to unravel. So I'm deeply impressed by biologists and evolutionary anthropologists.
Me too. And what non-physics science do you keep an eye on?
So in the podcast, actually, we talk about physics, but lots of biology as well.
Okay.
Yeah, because my co-host Kelly is a biologist. So we cover all sorts of topics in biology. I'm constantly learning about, parasites and evolution and all sorts of fascinating stuff. I feel like if I had 10 lifetimes, I would go into lots of different areas, maybe not even always physics.
Okay, we're getting ready to wrap up, but I need to know why did you write the book? Do aliens speak physics? What gave you that spark?
I've always been interested in this question of like the philosophy behind physics. Why do we ask these questions? What do they mean? And the questions are exciting because of their philosophical context. Like, like, is the Higgs boson really there? I want to know the answer to that question. That's a philosophy question. I want to know the answer. And I long believed that it was. I long believed that our physics was singular, that it was unique, that it was inevitable, that it was the only way to describe the universe. But then I started reading philosophy, and I became educated, and I understood, wow, there's a much broader context here. Some of these questions are much more subtle than I understood. And I wanted to share that.
Hang on a second, though. That is a life-changing moment. So what's the emotional impact of that change? Doesn't your whole worldview shatter?
Yeah, absolutely. I used to certainly believe that the universe was mathematical. I had that spiritual moment as an undergrad, and I believed for a long time. But, I got to UC Irvine, and they have a great philosophy department, and they give really interesting seminars, and I started attending those and paying attention, and then realizing, wow, I have a narrow view of this. And after a while, they started asking, like, who are you and why are you coming to our seminars? Actually, it happened after I discovered that there's a big cultural difference between physics and philosophy. In a physics seminar, you're explaining your science, you expect to be interrupted with questions. If you get to the end of your seminar and nobody's asked anything, then either you've lost them or you've bored them. It's a huge disaster. In philosophy, you do not interrupt with questions. I discovered only when I raised my hand and asked a question, and the whole room turned around and went like, oh my gosh. It's like objecting at a wedding, right? You just don't do it unless you got really something serious to say. You hold your questions to the end, and then you all discuss it. So I learned there's a cultural difference, but I met a lot of great people and learned a lot about philosophy. And so this book is about the boundaries of physics and philosophy that I think are not widely enough understood. And I wanted to share that with everybody, including a lot of my physics colleagues, but also everybody out there. There's not a lot of like accessible books about philosophy of science. And it's really fun stuff. It's mind-blowing stuff. It's deeply impactful stuff. But I also wanted to collaborate with Andy Warner. He's one of my favorite nonfiction cartoonists.
He's great.
He's great. He's written lots of great books. And I saw his stuff and I emailed him and said, hey, want to do a book about aliens? And to my surprise, he wrote me right back.
You're a vicious emailer, just audacious.
Cold emails have gotten me far, yes.
So, last thing, because you had such a seismic change. What would you go back and tell your younger self just getting into physics for the first time? And I know I think you worked in plasma physics for a while and finally settled on particle.
Yeah.
We'd all love to go back to our 21-year-old and tell them some things, but what would you say to yourself?
Well, look, I got no complaints. I think things worked out pretty well for me.
Fair
So
enough.
I'm very happy with how things turned out. I wouldn't change anything for fear of messing up something that's wonderful in my life. But I think the lesson is you got to listen to yourself. You got to listen to that part inside you that says, this is what I want, or this is not really working. I did a lot of different kinds of physics, plasma physics, solid state physics, that I thought I should be interested in. I thought I would be interested in, but my heart wasn't in it. And there's no good reason for that or bad reason for that. It's not bad or good. It's all subjective. And I tell students who come to work with me, I say, if you're bored, pay attention and go find something that isn't boring to you. Find the thing that grabs you, that makes you think, this is the thing I want to do. Because the whole job in life, science or not, is to figure out who are you? What drives you? What's your passion? And that's also true in science. You got to find the thing where you're excited about the big picture questions, but also enjoy the day-to-day work. Not easy to figure out. So only possible if you really pay attention to that voice inside you that says, this is your thing, or this is not really your thing. Go find something else.
It's a great lesson. Daniel Whiteson was here, everybody. The book is Do Aliens Speak Physics? The book is great. It's super fun.
Thank you.
I was surprised. I got on my Kindle, got into it, and I'm like, there's cartoons in this. I can handle this. It was really funny. So
Thank you.
I love it. Thanks for coming in. This has been a joy.
Thanks very much. Super fun conversation.
Thank you. Bye, everybody.
That was Daniel Whiteson. Very nice guy, really smart. Not much to analyze here. Daniel's credentials are bulletproof. PhD from Berkeley, Fulbright at the Niels Bohr Institute. He's been on the Atlas detector at CERN since 2007, and he was part of the team that confirmed the Higgs boson in 2012. He's elected fellow of the American Physical Society, and his books have been translated into 23 languages. The guy is the real deal. And the numbers he threw around, those are real. 95% of the universe is dark matter and dark energy. What's that? We've confirmed dark matter through galaxy rotation curves, gravitational lensing, and the cosmic background microwave radiation. So we know it's there, we just have no idea what it is. Every direct detection experiment, xenon, super CDMS, the LHC itself, empty. Nothing. They haven't detected anything. He talked about the Amateur particle. That's real, published in Science in 2023. A cosmic ray with 244 exa-electron volts of energy. Exa. That's millions of times more energetic than anything that the Large Collider can produce. And when they traced it back to where it came from, the local void, empty space. There's nothing there that should be capable of producing anything close to that kind of energy, and no one knows why. And then there's this idea that your phone can detect those particles. Crayfus, cosmic rays found in smartphones. He built a working prototype. The camera sensor in your phone uses the same silicon technology as the detectors in CERN. Put your phone face down on a table, a muon passes through. The camera picks it up. Get 5 or 10 million phones running that app at night, and you've got a cosmic ray telescope the size of the Earth. The Julian Swinger Foundation funded it in 2025 after the NSF passed. It's not science fiction, it's just underfunded. Then there's the other stuff. Hartree Field, the philosopher Daniel mentioned. He actually rederived Newtonian gravity without using numbers. No equations, no fields, just relationships, closer, farther, more or less. And it works. It means math might not be the language of the universe. It just might be a shortcut. And if that's true, then when Daniel asks whether aliens would do physics the same way we do, the answer might really be no. Not because they're wrong, because our map of the universe might be shaped more by our brains than by reality. That's something I hadn't considered before. We've got a model that predicts experimental results to 9 decimal places. And Daniel had a moment as an undergrad where he saw that precision and thought he was looking at the face of the universe itself. Then he spent the next 20 years learning philosophy and realized, maybe not. Maybe that precision just means our map is really, really good. It doesn't prove the territory looks the same. Daniel is one of those rare scientists who's done the hard work and still has the courage to say, we might be thinking about this wrong. Not from the outside, but from inside the machine. And that takes guts. His book is Do Aliens Speak Physics, co-written with cartoonist Andy Warner. Grab it from Amazon. It's surprisingly fun and funny and approachable. You can find Daniel on X at Daniel Whiteson. His podcast with Kelly Wienersmith is Daniel and Kelly's Extraordinary Universe. It's also worth your time. And if you want more on the simulation question that Daniel and I got into, I did a whole episode on that. We live in a simulation. If this conversation got you thinking about what's real and what's just a model, That episode won't answer your question, but it might get you thinking differently about our reality. Until next time, be safe, be kind, and know that you are appreciated.
In Area 51, a secret code inside the Bible said I would. I love my UFOs and paranormal fun, as well as music, so I'm singing it like I should. But then another conspiracy theory becomes the truth, my friends, and it never ends. No, it never ends. I feel the crap cat and got stuck inside Mel's hole with MK Ultra being only too aware. Did Stanley Kubrick fake the moon landing alone on a film set, or were the shadow people there? The Roswell aliens just fought the smiling man, I'm told, and his name was Cold. And I can't believe I'm dancing with the fishes. Hecklefish on Thursday nights with AJ2, and Wi-Fi's helping me all through the night. All I ever wanted was to just hear the truth, so the Wi-Fi's helping me all through the night. The Mothman sightings and the solar storm still come to Agatha, the secret city underground. Mysterious number stations, planet Serpo 2, Project Stargate, and what the Dark Watchers found. We're in a simulation, don't you worry.